This one connected, your Wi-Fi connected.
Hi, Dr. Bharat, can you hear me now?
Yeah. Myself, Sumer, I can hear you, sir.
Okay, thank you.
Yeah. So we'll just start in some time.
Yeah, okay. Now, I will be controlling my presentation, and
we'll start at 9:30, sir.
Right. No, I know.
Yeah.
But I just want to clarify that that both the video. I mean, would there be two channels where one I would present the video and the second channel is focused
it's
on
possible.
me?
Yeah, both possible.
So how do we do that? Or would you prefer only one where they just see the slide or my screen?
Anything which is comfortable to you, sir.
I'm okay either way, whatever the mode of, whatever your normal mode is, I'm okay with that.
Sure.
You let me know what you prefer.
Yeah.
We never got to do the rehearsal, huh?
Yeah. That was there.
Yeah.
So am I visible, right? And the screen is also visible, sir? With
yes.
background PPT on.
Yes,
okay.
I can see you, and I
so
can see.
I think we can start now. It's already time. So welcome you all for this short-term training program on modern computational fluid dynamics with industrial and environmental applications, which is running from today to Friday for 5 days. And we have very good renowned resource persons, Dr. Akshai Runchal from ACRI USA, Professor Murali Damodaran from NUS Singapore, Dr. Madhukar M. Rao from ACRI, Mr. Chakrapani from ACRI, Mr. Raj Gopal from ACRI, Professor M. Shekhar from IISc Bangalore, Professor Prabhu Ramchandran from IIT Bombay, Professor Ashok Dey from IIT Kanpur, Professor Amaresh Dalal from IIT Guwahati, Professor Manas Das from IIT Guwahati, and Professor Pradeep Kumar from IIT Mandi, and myself. So over the period of this 50 years, around 50 years of CFD, there is a large body of literature evolved into something which we call now a modern. So the aim of this short-term training program is to discuss all these modern techniques which are based on finite volume methods, starting from high-end applications from industry and the environment to the machine learning in fluid mechanics and heat transfer. So I hope that this particular short-term training program will be successful in providing its intended purpose, and all the participants coming from all over the part of the India, they will be greatly helpful out of this training program. I think our HOD, Department of Mechanical Engineering, NIT Calicut, he is also present. I think I would request him to say a few words. And
Sumer, can you just elaborate on the participants also? You heard about the speakers?
Yeah,
what about the participants?
We have around 30 students participants, and 10 participants from industries, and 6 participants from the academia.
Which are that generally, can you name few of them, main institutes as well as industries?
Yeah, I'll
Just to get a feel.
yeah.
You can just tell the general one. Need not be all the persons from where they are coming in.
Yeah, so I have to just
Or if you have the list, you can just project that.
yeah, I'll
so
just
that will
project
help
that
us.
list. Yeah.
So that even speakers also will be knowing, you get an idea about who are the
Yeah,
listeners.
sure. Yeah, so we have
Can you make it bigger? Can you
yeah.
just enlarge it little more,
Is it fine now?
little more, and then you can just tell institutes quickly. That's it.
Yeah. Mr. Abhishek Sarath, Mr. Ajin Jacob, Mr. Akarsh.
No, I think you can just tell the institutes. You not name all the institutes.
Yeah, so we have the participants from NIT Calicut, we have participants from College of Engineering Trivandrum, IIT ISM Dhanbad, and we have Amrita Vishwavidyapitam and Coimbatore Institute of Technology, Tamil Nadu. We have faculties from GB Pant University, Agriculture and Technology, Pantanagar, and we have 3 faculties from Manipal Institute of Technology, Manipal, and 1 faculty from NIT Calicut, and 1 faculty from Nitya Meenakshi Institute of Technology, Bangalore. And we have industry participants, 5 participants from Nuclear Power Corporation of India Limited, Mumbai, and 5 participants from BEML, Bangalore.
Okay, fine. That's all. Okay, fine. Thank you. Okay, let me come to my part. I am Jos Matthew, Head of the Department of Mechanical Engineering, NIT Calicut. On behalf of NIT Calicut, Department of Mechanical Engineering, let me first congratulate Dr. Sumir for arranging this wonderful short-time course that is very much relevant to industry as well as academia. So he did a wonderful work, and I first let me congratulate him for having done this excellent work. And then I wish this program a good success. And let me invite, wish all the participants also a good time. I am sure that you'll gain a lot during this 5-day program. I thank all the distinguished speakers who came from all over India, distinguished people, and even from abroad. I can understand that Dr. Akshai is from USA. Thank you, sir, for sparing your valuable time, spending time with us to share your expertise to the states as our new budding engineers. This new area, it's not new. In fact, you know that when I come from long time back in 88, you know, Finite, these are so popular earlier. Now you need to support with several applications, and lot of new software are coming with them. And when you open software, I can understand that you are getting exposed to the open source software. You know, there are many popular softwares. Let me say a few words about our department. NIT Calicut, NIT Calicut is one of the technologies in India, and we are one of the earlier institutes and NITs. And now the mechanical department is again one of the oldest and the largest department in the institute. We have around 42 faculties and around 4,000 students with us. We are running 2 UG programs, BTech in Mechanical Engineering and BTech in Production Engineering. And the total strength is around 300. And we are running at 5 PG programs. MTech in Industrial Management, MTech in Thermal Engineering, MTech in Energy Engineering and Management, MTech in Manufacturing Science, MTech in Material Science and Technology, and MTech in Machine Design. So that the total strength is around 130. So this is background. And regarding these courses, I can tell you Prof, that we are having these courses, analytical methods and predictable method, CFDs, all this part of our regular course, including the UG as well as PE courses. And we conduct many of the research in this area. So, and we have a good campaign software, even the departments and labs also, CFD labs are there. We have very popular software resources there, and we train our students free for all these softwares. We conduct free training programs to our students so that they'll get exposed to these techniques, methods, during their graduation as well as post graduation. So we are very much comfortable, and then we are happy. And now we are getting a host of a dozen of eminent speakers with us to share further to enlighten the knowledge of the CFD. And I'm happy that most of our PhD students in the NIT Calcutta is also attending that. I'm sure it will be beneficial for them. And if you would have been here, it would have been a pleasure to see you all in face. But now it's not possible. Still, we can manage that. So I once again thank all the listening speakers and all the participants, and wish you all a wonderful time. And I'll be back again to the last validity sessions. And I'm sure that Sumir will take care of you for all your needs. Please try your level best to learn what's the person from our eminent speakers. Okay, I wish the program good success. Thank you.
Thank you, HOD sir, for your kind words. And now the floor is open for the start. And I request Dr. Akshai Runchal to start his presentation and enhance our understanding and general description about finite volume method and governing equations.
Any advice? It says to present entire screen, a window, or a tab. I guess a window.
Yeah, you have to go for a present now and then the full screen.
Full
and
screen?
there, yeah, and you make your presentation full screen. You can type F5.
F5
to make your PPTs as full screen, and you can start. You are not audible, sir. You have switched off your mic.
Sir, you can unmute Dr. Akshay. Okay.
Yeah, I have made it.
Can you hear me?
Yeah, now we can hear you, sir.
Okay. So I'm doing present now, and then I say entire screen, correct?
Yes, sir.
And then I say share.
Yeah. Yeah, it's coming, sir.
Okay. And then I had my presentation.
Yeah.
Can you see it now?
Yeah. So yeah, you can start. Yeah.
Okay.
Wonderful.
All right.
Yeah. All right.
Okay. What I'm going to present is actually three things: a brief history of computational fluid dynamics, and then a little bit of the equations, and a little bit of the finite volume method. My name is Akshai Runchal, and I've been in the CFD field for most of my life, and it's a privilege and a pleasure. So thank you very much, Sumerji, for inviting us. And I welcome all the participants, and I hope what I'm going to say would be of some interest to you. So let's first see, my Professor Spalding was very active in this field, and he used to say that we inhabit fluids and fluids inhabit us. We're surrounded by air, which is a fluid, of course, and 2/3 of Earth's surface is water, and 2/3 of human body is also either air or water. So CFD is very pertinent to both our environment, our existence, as well as ourselves. It's a very challenging issue, and it presents the most complex and interesting problems. And for me, it has been fun, and I hope it is for you too. This is a nice place I come from. It's called McLeodganj in Himachal, Dharamshala. And I show it to you because it's a nice place to be, to think, and to be grown in. And by birth of accident, I was here. So growing up in these hills, I never thought I'll be part of a birth of a new branch of engineering called computational fluid dynamics, but that's what happened. It happened at Imperial College. And I also never thought that this place, where there were only 3 families that lived when I was a child, will become the home of Dalai Lama and will lead to revival of Buddhism as well as human rights movement, and would be on the political maps of India, China, and the United States. So I'm a lucky man. I was at the right place at the right time, and can't debate that. So here is some of the dates that are important in the CFD. The first commercial computer or semi-commercial defense computer was the IBM 701 that was introduced in 52. In 55, there was a very brilliant scientist, Frank Harlow, at Los Alamos National Lab, which was a defense and atomic weapons lab. He started working on fluid dynamic problems. In 60, the Dalai Lama arrived at Dharamshala, and I left for to do my graduate program in Chandigarh in engineering. And also Brian Spalding started working on his unified theory, which played a major role in the Imperial College approach of computational fluid dynamics. So in 65, Brian Spalding actually started working on the finite volume method. It took about 4 or 5 years playing and doing different things. And then we came upon the finite volume method. And 69, CFD was already a practical tool, and it was being used for many practical problems. So over a short span of about 2 decades, from the computers that came to the CFD, it took. And so it's about 70, what's it, about 50 years now since that time. Before we could have computational fluid dynamics, the mathematicians had already laid the foundations of tool that would be very useful. That always happens in science. A new development or a new invention or a new technique comes, and usually it's, you know, as Newton said, you stand on the shoulder of giants and see further out. So finite difference method had already been invented by the mathematicians. So was the concept of numerical analysis, matrix theory, and most important was the minimization principles, which basically say that the most physical systems try to seek their minimum energy status, and that leads to what's called the Hamiltonian or the variational methods. Also then more recently, this happened in the last 200 years, but more recently, Richardson and Quorum and his associates made some very good contribution to that, eventually led to CFD. So you might say that the basis of CFD goes to about 100 years. Believe it or not, before there was electronic computer, people were already doing what would be today called CFD. Thom was one of the pioneers in this field, and he obtained a finite difference solution for a flow past a cylinder at a very low Reynolds rate, about 50, Reynolds number of 50. And he found that beyond 50, his solution will not be stable. He had used what's called the stream function of vorticity method, which was the first method that was used for the computational fluid dynamics. Southwell developed the residual relaxation methods for elliptical problems, which became very important, very interesting. In Allen and Southwell then obtained solutions of flow, which went up to a passed the cylinder up to 1,000 Reynolds number. And then there were people like Tom and Apple, Kawaguchi, Simony, a bunch of others. And basically these calculations were done by hand, adding all numbers by hand. If you can imagine doing a computational fluid dynamics problem today when you don't have an electronic computer. So the birth of CFD can be attributed to brilliant scientists. One was Frank Harlow at Los Alamos. This happened in the late 50s, as I said, and Alamos got its first IBM in 1953. And then Brian Spalding, once the IBM 7090, which was the next generation IBM that came to Imperial College. As happens often in science, both of them worked independently without knowing much about each other's work till it was almost done. But Spalding, out of the two, Harlow was a scientist, Spalding was an engineer, and that played a big role in their approach to CFD. Harlow was more interested in solving interesting problems, and for the sheer joy of it, he was not interested in applying it to industrial or practical problems. Spalding, on the other hand, was an engineer, and he wanted to make it a common tool, and that's what happened. So, just to put things in perspective, what a difference from today. The IBM 701, the first calculator, had 2K words, if you can believe, 2K words of 36 bit, which is about less than 10 kilobytes of memory. And the memory could be expanded to 4,000 maximum, okay? Today, you could not even write an app in that. The cycle time was 12 microseconds, okay? Microseconds. Today, we're talking of gigahertz, 10 to the 9s and teraflops. This is 10 to the 6. Just an addition required 60 microseconds. Okay. Today we do a 10 to the 12 such operations in a second. So the factor of 10 to the 4 in cycle time and 10 to the 8 in memory and speed has occurred. If you can imagine that in this short span from 1952 to today. So 7090, that was the first computer I worked on. This was a transistorized version, and it cost about 3 million and filled a whole room. I remember we used to go and physically load tapes on it. Okay. It had a memory, amazing amount of memory of 32,000 words, 32K words. And the basic memory cycle had been cut down by a factor of 6 from 12 to 2 microseconds. But the interesting thing that 7094 did was that it introduced a double precision floating point, which came very handy in the CFD in the later days, and today you can't manage without it. So what led to CFD Imperial College was that Spalding had already worked on a common format for flow, heat transfer, and mass transfer. Before Spalding, people thought of fluid flow as a different problem. There were fluid mechanics people dealing with it. Heat transfers were dealt with people in the heat transfer field, and mass transfer was dealt with chemists. But he saw that the underlying mathematics had great similarities and that they were really no different from each other. And so he came up with a universal unified theory of boundary layer jets and wakes, which played a big role in solving many practical problems over a period of 10 years. He also was an engineer. He knew the uncertainties that we faced in dealing with turbulence, which were the most important problems. So he instituted a number of his students to collect all the experimental data and try to find out a universality in the constants that were needed for turbulence. And finally, he made some very innovative theoretical and experimental contributions in droplets. There is even a B factor Spalding number that was designed for that. So these will prove very crucial in computational fluid dynamics and became to be called Imperial College approach. So before computational fluid dynamics, as everyone knows, I'm not going to repeat it too much, dwell on it too much, the Navier-Stokes equations are the hardest equation to solve, which govern the fluid flow. There is even $1 million prize today if somebody can find an exact solution of Navier-Stokes equations. So what people did was they assumed that a flow behaved in a self-similar fashion. What that means is that if we determine the velocity profile at one time, like in a tube, it's a parabolic profile, then it stays parabolic throughout the pipe. So what you did was you assumed a parabolic profile, you put it in the governing equations, and then there were some unknown constants that will arrive, and then you match those constants to the initial and boundary conditions and solve your problem that way, which is very specific. You had to find a profile for each application, and you had to have the boundary initial conditions, so there were only so many. You can't have too much flexibility in the profile. It was very cumbersome. And then the worst thing was that actually most flows of practical interest were not self-similar in those days, and they are not today. So with working with a brilliant student, Suhas Patankar, Spalding worked on generalizing the profile method. They said, okay, let's assume the analytical profile that people used to do, log law or some kind of a exponential or some kind of a series polynomial. Let's replace it with a piecewise polynomial, such as a linear even. Okay. So in other words, the profile was not made throughout the profile as one analytical shape, but it was a piecewise with different linear profile. I mean, you know, any curve can be fitted with small amount of linear segments to a reasonable accuracy. So the advantage of this was that you no longer had to find a adder profile. So this was also very similar to finite difference approach, though we didn't realize at that time. So in late 64 and 65, Patankar developed an integral profile boundary layer code, which was a nice breakthrough to solve boundary layer code problem. The problem was that this approach of a profile, as I said, did not work for recirculating flows or flows with highly curved streamlines. So myself and Micha Wolfstein were other two students working at the same time with Brian Spalding. Suhas was working on wakes and jets and boundary layer flows, and he had asked me to work on recirculating flows. And the third more important class of flows are what are called impinging flows, where like a jet hits a wall. So he had asked Micha Wolfstein to work on that. So we were all three working in parallel, but on each subclass of problems. So he said, hey, Patankar has come up with a nice method. Why don't you use it for your problem? So Micha Wolfstein and we started using that, and we found that boundary layer is destroyed by an adverse pressure gradient, which occurs during these two kind of flows, and you know, and you can't use those problems either for the impinging jets or for the backward facing step or for the square cavity on which I was working. So these extensions were firmly established universal theory, but the parabolic flows were different from elliptical flows, which had strong pressure gradients, and it just did not work for us. So we decided to explore something else, and we said, okay, I went to the mathematics department and said, what can I do? They said, well, try the finite difference method, and we switched to that. So we started working with finite difference method. So after a while, Wolfstein and I realized that we were essentially using the same approach on different problems. We were sharing the same numerical instability for higher number flows, and that we found later that this was related to not having a positive definite matrix for a system of equations. We also realized that the positive definite matrix is destroyed because of something called the non-upwinding of the flow. What happens is that if the flow comes from a certain direction, it has a strong properties of that direction that it carries. The differences, central differences, assume that everything is neutral. All directions are neutral, and that what comes from down, what comes from up. So central differences have no concept of up and down, but the flow has a memory of up and down. So there was a conflict between the physics of the memory and the mathematics of the finite difference method. So Spalding made this analogy, and he said, well, let's go to a different direction. And he said, let's not think of this as a simple problem for math. Let's think of it as a physics problem where we have flow going from one tank to another. And I'll show you in a minute what he had an idea. And this is what led us to the finite volume method. And eventually, we found that this method freed us from the computation of thinking in terms of kind of finite differences, and now we thought of integrating equation rather than differentiating. So we did not have to use the Taylor series for that. So we started assembling this code, and then that code became the standard code for Imperial College, and also it was in our book. So it has become the basis for many courses that time. So this is basically, you might look upon it as a finite difference grid, where these are kind of your center points and these are grid lines. Or you can look upon it as Spalding did. He said, well, these are a bunch of tanks that hold the fluid. It comes from this pipe, it goes out from this pipe and goes to the north face. So now we can decide how much goes from P to N, from this point to the north face, and what comes in. Or of course it can reverse direction and all that. But basically the concept is that you don't look upon this as a finite difference grid. You look upon it as a series of holding tanks and things flowing between them. Now, main difference is that this is now all measurable quantity. You can measure how much flux comes out of a tank, how much flow comes out of a tank, how much heat comes out of a tank, how much mass comes out of a tank. So you don't have to, no longer the focus is not on things like velocities and pressures and all that, though they play a role. The focus is on engineering quantities which can be measured. So this was a great breakthrough in thinking, and this is why it's a finite volume. Each tank has a finite volume. It receives flow from its neighboring tanks and transmits it to neighboring tanks. So this scheme eventually led to the upstreaming, and then we also found there were some issues with numerical diffusion, which become which you all are now, I'm sure, wise about, and that's why we developed higher order schemes. But the most important thing was that at that time I realized that rather than doing the differential approach of using Taylor series like in finite difference, for the finite volume, you could use the Gauss theorem, because now you can integrate things around each tank and say how much comes in, how much goes out. So this was called the integral approach. This has been kind of a classical fight between the differential approach of Newton and integral approach of Leibniz in France, and they called about it for a long time. Both have their validity. But I think the integral approach is very, very important for fluid dynamics. Of course, you can derive equations from either of those, which are the same, but it's just a thought, because the focus is not on mathematics now. Focus is on the physics of the problem. How much flow comes out of one, how much goes to the other, what pressure it has, how much heat transfer, what temperature it has, things of that nature. So by the end of '69, we had realized the importance of commercial potential developments applying to particular problems. So we organized a post-experience course at Imperial College, just like the one you're attending today. Of course, this was more interaction, pre-COVID days. And Brian Spalding actually started a commercial company called CHAM, which is still around. And the academic press published our book, Heat and Mass Transfer in Reciprocal Flow, which was a classic at that time in '69. It's the first book properly in CFD. Sam Pun took over the phone because I was coming to I was coming to IIT Kanpur to teach, and Suhas had left also for IIT Kanpur, and Mika had gone back to Israel, so there was nobody there. So Sam Pun took one, and he's one of the co-authors for that reason. Brian had a strict rule that all joint publications carry the names of the alphabetic order. That's why people ask me, how come Gosman's name comes first in the book, when he wasn't even part of doing any CFD at that time, though he did quite a bit of work later. And it's because in Imperial College, if you look at Spalding's publications, they'll always be in alphabetic order, which was, I think, a good rule. So '69 to me was the birth of the CFD, and it ushered in CFD as an engineering tool, and then it was, greatly expanded. Okay, so around 70, so far we've been using stream function vorticity approach. We realized that this approach is not going to work very well for three-dimensional flows. So we had to go back to primitive variables. Primitive, we mean U, V, W, and pressure, things of that sort. And Cholesky had already pointed out that pressure can be replaced with any scalar with pressure decoupling equation. This happens in the fluid equation because there is a pressure is a scalar quantity, flow velocity is a vector quantity. So the velocity is determined by a component of the flow, the vorticity, which is a vector quantity. Pressure depends upon a scalar, a potential. So the velocity at any stage can be determined as a component of pressure and as a component of a vector, which is the vorticity component. So Patankar and Spalding had already used this approach of splitting for parabolic flows, but they had not used it for general flows or elliptical flows. So Harlow also had introduced a staggered grade and a decoupled pressure, the Cholesky approach, for multidimensional flow. So basically, Patankar and Spalding borrowed from these and combined them to create something called simple. So in 72 it happened, and then this basically simple was a revolution in CFD practice, and most successful codes today employ variants of simple or some approach which has its origins in this one. So actually the basic approach of pressure splitting goes back to Cholesky and to Harlow, who had used it. Turbulence models play a very important role, and Spalding knew that practical flow computations will not be possible without turbulence. So, and of course, there are a lot of problems. Energy is a big area even today. Chemical reactions take place everywhere. So we needed to take a handle on those too. So based on this work, he started working on the turbulence, and we started borrowing from the work of Kolmogorov, Prantl, Chow, and Rota, and number of models were tried by different students of Spalding's and Launder's group. And we already had the universal constant that Spalding had derived from his universal theory days. So Harlow published a paper on K-epsilon model, and Launder and Spalding decided that this was the preferred tool, and turbulence became a problem that won. Then the other thing was combustion. So here the breakthrough came when Spalding published a paper which introduced the concept of eddy breakup, which took account of the intermittency of turbulence and the reaction rate of turbulence. Because what happens in turbulence is that two species may be present simultaneously, but they may not be present at the same time. Okay. So for them to react, they have to come together, and they may be sitting in different eddies. So if you have a laminar flow, then these two species are everywhere and can interact with each other freely. But if it's a turbulent flow, there is the problem of intermittency. That's because one species is caught in one eddy, other species caught in other eddy. So that was the problem that Spalding solved with the eddy breakup model, and this became the first multi-fluid model, and it made combustion computations practical. So between 65 and 75, just to give you an idea, there were perhaps more than 40 students and faculty working on the wide range of problems, experimental, practical, in one place at one time. That is perhaps not even today that you have 40 people working in CFD in any department even today. So that was the situation. We used to have our only weekly seminars, so every student was asked to present his ideas, once in a while. So it was the largest CFD group at that time, and even today, I doubt there is a larger group. The other group was at T3, but that was much smaller than the Imperial College group, about 10 people. So Spalding and his students basically used it because Los Alamos was a national lab. It was a secret lab in those days. You could not even publish their work without getting permission from the government. So their work did not come into the practical domain and till another 2 decades or so before their reports became very popular. So CFD tools came out of Imperial College, and then at that time we also had LDA came out in the same time, and Jim Whitelaw was working on it and on turbulence focus. So the number of people who then we were in touch with, and I think you will have these slides, so I'm not going to go through them in interest of time, but that's that's how very quickly the CFD technology spread throughout the work. One question people always ask me is that what's the difference, or what's better, finite volume or finite element? So we interacted with finite element, which also developed about the same time. At the original, one of the first person in this field was Argyris, who was in Germany and then came to Imperial College, and then it was his student Zienkiewicz who went to Swansea to set up the whole group there. So finite element had some advantages because it had for structures it had been very successful, but we realized that it was unsuitable for high neuronal flows in that form as it was in those days in 60s and 70s. Okay, because it had Hamiltonian does not exist for nonlinear equations, and structural problems are linear, or at least elastic structure problems are linear, and the fluid equations are nonlinear. Also, the plastic structural equations are nonlinear. So we had to find some different thing than Hamiltonian to minimize the energy, because there are multiple minima and you must select one which suits you. So there were some problems with that. The big problem with finite element is that finite element uses a variational approach and then solves it in a manner where you minimize an integral of some kind over the whole domain. Let's say you minimize the error. So the error over the whole domain is minimized. It does not assure you that the error is equally distributed. So error could be very small for 1 million nodes, but all of it could be present in one node. And that is not very good for things which such a nonlinear things such as combustion or other things. So even today, you'll find there is no really successful method for combustion that is based upon finite elements. So overall, I personally prefer the finite volume, though you can derive the basic equations from each method. And the main reason is that finite volume allows you to minimize your error at each point. Finite element does not. So just to tell you that there was what we were doing, we didn't know this was called CFD. CFD term did not come till Pat Roche from Sandia wrote a book called Computational Fluid Dynamics. It's 72. That book is not very well known. It's out of print today, but that's the origin of the name CFD. Okay, so we were just using it. We said, hey, we're solving the fluid dynamics problem. We didn't know it was called computational fluid dynamics. So that's what happens. So the main thing about the Imperial College approach is that it unifies flow, heat, and mass transport in a single framework, and its focus is on physics, that is the engineering interest, rather than on mathematics. So that's basically what it is, and these are some of the things Spalding was fond of saying, and one of it is he's very fond of saying they can because they don't know they can't. Okay, so this is like climbing a mountain, not knowing how to climb a mountain, but you make a good effort and you succeed sometimes. So let me move in the interest of time to the governing equations of fluid dynamics. So what I'm going to show you is a simple approach. I'm not going to get into the details of the nitty-gritty. I'll leave that to the next speakers or to your regular CFD course. But the governing equation of fluid dynamics are two kinds. One are called the balance equations. These are principles of mass conservation, like the continuity equation, or principle of momentum balance that leads to Navier-Stokes equations. The first law of thermodynamics that leads to the thermal energy equation, and species conservation principle that leads to the species transport equations, right? So these are balance equations where some quantity is kept in place, balanced, is not, if it's not destroyed or created, it's a balance between different components. It can only be transported, moved around and all that. Like, you don't actually transport. I mean, if you're non-relativistic, you don't actually create matter. There is matter. Okay, you can move it from one place to another, but you can't create it. Of course, you can destroy it, get the energy, and then you're in the relativistic space. So then there are auxiliary equations we need to solve. For example, we need the density relations. Gas law is there. Okay, this is called equation of state. Or there is a constitutive relation like viscosity, turbulence. Okay, fluid property relation, thermal conductivity, host media. For example, porosity in case of groundwater flow, or in case of interaction, fluid structure interaction, the properties of the structure which is the host media. So these are two classes of equations that govern flow. So let's look at the balance equation. Okay, so let's look at any arbitrary control volume, and what I'm going to show you a very simple way, it's no different than keeping your bank balance, is that if you have a volume, a given arbitrary volume, and it has a surface, it's bound by a continuous surface. Okay, that's the important thing. You have a volume, a surface, like your glass, okay, or any container. Okay, now the only way things can change, accumulate in this volume, okay, let's say you have X amount of some quantity, how does it become from X to Y? So what can happen? Either it can be generated inside this volume, or it can flow in or out of that volume. There is nothing else that can happen to it. Okay, so it's a very simple concept. It's very simple way to remember equations. Okay, they are nothing but that the rate of accumulation is the net influx through the surface plus net rate of generation. There is no other change, right? It's like your bank balance. You have a bank balance. How does the amount grow in it? Well, you either put your salary in it, or you take your expenses out, or you get interest, which is generation inside. Okay, nothing else can happen to the bank account, right? Okay, well, except from spammers getting it, which is flux, illegal flux. So that's what happens. So that's the basic concept. Now let's see what is the rate of accumulation. A rate of accumulation in this volume is basically, there is a certain amount phi which is inside. Okay, this phi is the total amount inside. It's so many kilograms of matter, and integral over this volume gives you the total. Now d by dt of that is the rate of change, right? That's how it can change. You have the total volume, phi is the property, and you integral and you differentiate and you get with time and you get this. Okay, of course, as long as the volume is not changing a function of time, d by dt can be moved in. So the rate of accumulation is nothing but integral over volume of the rate of change of the property. Okay, now let's look at the next quantity. What is the flux? The outward flux from the volume, J, is basically directed in the normal direction. So you take the normal at each direction and you multiply the flux with that normal, J dot N, okay, and integrate over the area, and you get the total flux going out, right? If the velocity is going out here, you take this little segment, you multiply by this velocity, property moved this area. This velocity, this area, this velocity, this area. That's how much mass is going out. Of course, that's there, right? So that's J dot N dA, and G is the rate of generation, okay, inside the volume, and that is basically just the integral of that G. As simple as that. So the balance equation is basically accumulation, net influx, and net generation, okay, which is combination. They could be destroyed also, so that's a sink, but we are taking the net. Okay, similarly, this is net inflow. Some flux is going out, some going in, but we want the net inflow, and that leads to the influx. Now, if we use Gauss theorem now, we get this equation. Okay, basically Gauss equation as delta V goes to 0 tells you the d phi dt is del of J plus G. This transfer from here to here, from area to volume, is what is the Gauss theorem. Okay, so very simple, just like your bank account. Savings grow, income in, expenses out, or fluxes, and interest accumulates. So professors make it very difficult. And when I first learned one, I thought these are very complex equations. What are they doing and all that? And now I see how simple it really is, in fact. So what are those fluxes, that J quantity? Okay, So let's talk of most common fluxes are convection and diffusion. Convection is where something moves from point A to point B, and diffusion is where there is some uncertainties in the motion of this thing, and we determine it through the gradient of a scalar. Okay, so that's what a potential, as it call it. Okay, so radiation is another common flux for heat transfer, and there are many other types of fluxes. But let's talk of these two. They are the most important, the convection diffusion. So net outward convective flux at a boundary is basically just the rho times the property. Okay, it's the velocity times the property. That's all, right? Like if there are, let's say, 5 units of something being transported, okay, and the area is x, you do integral of 5 times the area of x. Okay, if they're moving 10 times every second, the velocity is 10, then you multiply by 10. Okay, so that's basically convection. Now diffusion is given by this quantity d phi by dx, and this is from Fourier's theorem and number of other one have seen that diffusion, first order diffusion, can be related to the gradient of a potential of that particular quantity. How it changes, slope of that transfer is what basically does the gradient. So the general transport equation, if we put in for J, which was the equation before, the J is being transported here, del dot J. So this now becomes del dot V because of this U times phi plus del dot gamma times delta of phi. Okay, so that's the general transport equation. We haven't said this is for momentum. We haven't said this is for temperature, for species. This is for anything that can be moved by convection and diffusion. If it moves some other ways, those terms will be added. So in this index notation, this transport equation can be written as accumulation, convection I've separated from diffusion on brought it to this side, convection out, diffusion in, sources which are of different kinds and have been generalized now because there are many kind of sources that we deal with. So this is a little more general in the sources. Okay, otherwise these terms are identical. Okay, so this equation in a general form was first Spalding's concept that all transport equations can be represented, heat, mass flow can be represented by this one single equation. So we didn't have to write the code for each different things. We wrote the code to solve this equation, and then we can do heat flow, mass flow, and momentum flow. Okay, so that's the general equation. So for example, for mass flow, this equation, continuity equation, you know, well known, and this is the equation for momentum in 2D, and the source term here is essentially due to pressure, okay, which for example is for the x direction component would be dp dx. Okay, that's the source for it. Of course it could have some other source momentum which we can add here, but pressure plays a role, and this is the gradient of pressure that leads to momentum. So this is basically the 2D form of the Navier-Stokes equations. So the common set of fluid dynamic equations you come across are the mass density, the u momentum, the y direction momentum, z direction momentum, the enthalpy, mass species of different kinds, and the kinetic energy turbulence, rate of dissipation, and frequency of turbulence. These are the common equations that you see, though now of course they're all kind of applications of CFD. So if you go to different problems, you'll have all kind of other equations and to enter and to solve. So let's spend the last few minutes on the finite volume method. I already introduced the concept of tank and tube for you. So what happens here? So in the computational CFD control volume approach, we don't have a grid per se. Grid comes as a grid comes as as kind of a secondary thing. We have a control volumes. So the field of interest is divided into control volumes, and it can be any arbitrary polygon, though I've shown you a simple one. And sorry about that. And basically look at this volume. There is typically a field node in this control volume, and this is somewhere placed somewhere in the middle, doesn't have to be the center, and they could have a boundary node. and it has general direction of flow. So this, of course, is simple illustration, but the numerical values are computed at these nodes. Boundary nodes are typically either specified or inferred from simple geometric relations, okay, from boundary conditions, okay? So the field nodes are the one. So for each control volume, this is the thing with the finite volume, that for each volume, there is only one field node. So imagine the tank. So this is the tank, and this is the average value in the tank, right? It is not like the finite element where an element can have multiple nodes, okay? So finite volume method has only one node per element, and that node represents the average state of fluid in that tank. It's not a point value. It's the average value. You have to be very aware of that, okay? So that's the main thing. Now let's look at a general form. It could be a polyhedral this way. Basically, you have a number of surfaces of this, right? Okay, there is all these surfaces that this control volume has, right? So it can be generalized. That's the beauty of it, without too much conceptual problem. Like if you generalize a finite element method, you create a lot of mathematical complexities for that, okay? But for finite volume, it's very easy to generalize from any kind of arbitrary volume, okay? So basically, all we're going to do is each is treated as a piecewise. Each surface has fluxes going through it, and whole of the control volume only has one point on it. So there's no points on these points, okay, at the boundaries, okay, except the boundary conditions which represent if this was a boundary node. In other words, so any volume has one node and surfaces around it, and basically we piecewise determine these surfaces. So this is the balance equation, and what we do is we take the average value in this tank and we say that is what it is, and write down a simple algebraic analog of that, okay? So for example, this equation becomes the equivalently is the 5 average times the volume times the delta T. Integral over that time is the amount of quantity in it, and this is the flux here, each flux, each area, integral over delta T. Generation for the volume over delta V and delta T, okay? This should be delta V. So JK here, this flux here, is basically again the velocity at that point and what it's carrying out times the property, and the gradient at that point, the difference from this point to that point, a difference between this and this point, and the gradient, normal gradient across that, as simple as that, okay? So basically we can write the flux as this value here of velocity times the property value carried out, and gamma at this point, the diffusivity, and the distance between the 2 points and the normal gradient between the 2 points, 5 outside, 5 outside. So it's a very, very simple concept. You don't need a high level of mathematics, okay? That's the main thing about the finite volume. So here is basically a Cartesian grid, and basically is the gradient points, and we take it shows the fluxes in, fluxes out, and no different than the complex one in the 2D case, okay? So you've already seen this. I'm not going to show this. This is one-dimensional flow. I'm going to take an example, okay? So there's only one x direction here, okay? And this is the simple equation, and J is this quantity for the one-dimensional equation, right? So I take a one flow here from this one, and this is basically the integral. It becomes the old value, new value minus the old value is the increase, right? The source is basically the average of the source for this node, okay? And the flux is basically dj dx, the gradient of the flux, okay? From Gauss theorem, we invert back. So actually you see that in finite volumes, we go back to the way we derive the equations to the root level, and we convert the volume back into the surface through the Gauss theorem, the inverse of what we did to derive the equation. So it's a much more natural way of thinking, okay? So this is the flux, and the flux can be written as, this flux can be written as the U at the east point times the value at the point, gradient between those 2 points, right? That's the flux going out, okay? As simple as that, Okay. So if we combine all this, and you can do this at home, you'll find that you can write a relation for phi e, which is a combination of the 2 points, right? In other words, we are saying that phi at this point is made up of a weighted average of these two, right? That's all that's saying. Okay, so that's what that means, that phi is a weighted average of phi e and phi p. Okay, so for central differences, this will be taken as half if the grid was uniform. For upwinding, it could be 1 or 0 depending on the velocity direction. Okay, so this is the flux becomes UE phi e minus gamma and times this thing, and you combine all these things and you get this equation. Okay, this equation can be simplified to say that it's a connecting coefficient CE for the east boundary. Okay, and the difference between phi p and phi e. Okay, again going back, it's the difference between the 2 points on the 2 sides. Okay, so this is the coefficient CE which connects these 2 points. Okay, and this is the center point. This coefficient is called a Peclet number and plays a very important role. Negative definite matrix that I non-positive definite matrix that I said becomes when alpha EPE becomes greater than 1, then this CE becomes negative. Okay, that is physically counterintuitive. Okay, that cannot happen in physics. Okay, so that's why this play is role. So alpha A must be selected so CE never becomes negative. Okay, so this is the Peclet number. That's the depend on the Peclet number, which is how fine the grid is, what the velocity is, what the diffusion coefficient is. So as phi E decreases, the flux should increase, right? Okay, because you're going from P to E. So as flux goes down, the flux should go in the direction of the decreasing gradient. Okay, so therefore the relation says that CE cannot be negative, therefore Peclet number must be less than 1 by E. So the problem that people were facing before upwinding was that for central differencing, alpha is half. So as soon as the Peclet number became 2, their problem became unstable. So this is the secret successful scheme. So it is only stable if Peclet number is less than 2. So one solution to use was to use upwinding scheme. So the basic idea was that when U is greater than 0, when flow goes this way, let's take the P value. When the flow comes back, let's take the E value, right? That's most likely, right? When the wind blows from east, it brings the properties from the east. Okay, so that's the idea. So this idea can be expressed in this form, and the east influence coefficient is this one. The problem with this approach is that it has a high numerical diffusion under certain flow conditions when the grid is not aligned with the direction of the flow. It works beautifully when the grid is aligned with the direction of flow and it's high and the velocity is high. It still works. So in 72, I came up with a hybrid scheme concept, which we said, well, why not rather than us choosing whether to use central or finite, why not let the computer code determine when Peclet number becomes greater than 2 or less. So inside each point, we monitor Peclet number. If it's less than 2, we use central finite differencing. If it is greater than 2, we use upwinding. Okay, so this should be the opposite sign, greater. So basically what this does is it delays the diffusion, the numerical diffusion to the point at those points where the grid is very coarse and where we cannot do it. Otherwise, for most of the grid points, you may use central differencing. So this turns out to be a lot more accurate, as that was shown. And actually, this is the scheme, some variation of which is the default scheme. At least till recently, it was in every code and was the most popular scheme, though now people are using higher order schemes such as Quake and TVD, and there are many schemes. So for those of you who are in the research field, there is no perfect scheme today. The primary requirements are the perfect scheme should be at least second order in space. It should lead to unconditionally positive definite, CE always 0. it's to preserve the extreme of neighbors. That means that phi E must lie between phi P and phi E and not automatically, kind of increase. And that the total flux surface must be same looking from both sides. So these are basic requirements of a scheme, and I think we want to get to this one day. Nobody has it today, so this is a good thing for you to work on. So combination of all these leads to a general matrix, okay, which represents sum over all the elements. If you have a million elements, you have a million equations, as simple as that. So you have to compute these, and the matrix form, it's like this. And just this is an example that I will show. Okay, so I hope I've done a decent job within the time of giving you an idea of the basic equations, of the basic finite volume method, and of the history of computational fluid dynamics. It's been a passion and profession for me for 55 years now, and I have enjoyed every single minute of it. So nothing is more challenging, and I think I'll hand over at this stage. Thank you very much to all of you, to the participants, to Calicut NIT for arranging it, and to all of you who made it possible, and all the research workers who had worked with me over the years. Thank you.
Thank you, Dr. Runchal. The participants can, if they have any doubts, they can ask the questions to Dr. Runchal. We'll be happy to answer. I think there was one question, I think, from Raj Gopal. Mr. Raj Gopal, I think he raised the hands in between.
No, that was accidentally raised.
Okay.
Sorry.
So anybody who want to interact with Dr. Runchal, he can interact. We still have 7 minutes.
Good morning, Dr. Runchal. This is Amaresh.
Hi, Amaresh ji. How are you?
Yeah, good. A very good morning to you and all the participants. So it was a nice talk. I also joined and listened, and maybe I will be also covering some part of it in my beginning of the lecture.
Good.
So I liked your this presentation. Thank you.
Thank you. Thank you. Thank you very much.
So you are in India right now, or in US?
No, I'm in India. I've been here since November of last year, and can't travel for perhaps another 4 months, 5 months. so I've been very much here.
Okay.
In a much more beautiful place than Guwahati, in my opinion. You saw my hillside there. I don't think you can match that in Guwahati, huh?
Your place is very nice, and
Yeah.
I wish to visit sometime after the situation becomes normal.
Sure. Most welcome.
Sir, good morning, sir.
Yeah, please. Sri Venkat. Yeah.
Yes, sir. Sir, it's a basic doubt. What is the difference between a property being convected or property being diffused?
Being convected and being diffused.
Yes, sir.
Yes. Okay. At the let's take viscosity, for example, or temperature. At the microscopic level, atomic level, or molecular level, there is no difference. Okay. Diffusion is basically our ignorance of the movement of a fluid, because what happens is that, let's say there's a Brownian motion in the fluid, right? So the particles are moving all the time, right? So convection is kind of a bulk macro movement where we physically pick up something and move it to the next place. That's convection. Now, what happens at the micro level is that there is a mean free length, which is very small, much smaller than the control volume we have, right? Mean mean free length of the motion will be much small. So the particles are moving all the time, but we don't know when they're crossing the control volume and when they are not. They're crossing the control volume, coming back, crossing the control volume, because their length is very small, right? So we cannot therefore either determine and put in their velocity. We'll have to go back to the to the Boltzmann equations and go back to the molecular level. If we wanted to do that, then there'll be no diffusion. But because we do not know how these particles are moving at the mean free length level, we therefore take an average of how they are moving in the bulk format, and so all the Brownian motion is integrated within the one, and the net movement out or in, which is always in the area of the gradient, is what happens. So what happens is that if you have a higher temperature, a lower temperature, the particles are not constantly moving from the higher to the low temperature. They're moving a little small distance, 10 to the minus 3, minus 4 millimeters, and then going back, then moving again, maybe this time 2 times 10 to the 3 millimeters, and like that, back and forth, back and forth. Like the best example is a drunken man going home, and there are a number of trees, and every time he falls down, he holds on the next tree. Then he doesn't remember which direction he's going. He goes to the next one, right? His average motion to the home is now not equal to distance to the home. He's traveled a lot more distance, right? So the difference between the two is the uncertainty, and that is expressed mathematically as a diffusion. So diffusion is almost always, with some exceptions, from a higher gradient value, a higher concentration, to a lower concentration. Convection can move either way based upon the velocity. Okay, convection can go from a lower to the higher one. You can force water into a tank which has less pressure, right, through pressure, right? But the diffusion is a process at a molecular level. At turbulence, that's why turbulence eddies move, and the equivalence between diffusivity due to turbulence and molecular diffusivity is simply this. Mathematically, molecular diffusivity depends upon the mean free length, and the turbulence diffusivity depends upon the size of the average size of the travel of the eddies. So I hope I answered your question.
Thank you, sir.
Hello, good morning, sir.
Good morning.
Yeah, sir, I have a small doubt. What is there any difference in stability and consistency? And the second question is, what are the factors that we need to consider while checking for stability or consistency?
Okay. Consistency and stability are two different concepts. Sometimes one guarantees the other. A consistent scheme can be stable, or a stable scheme can be consistent and not. So what happens, consistency is basically saying that the numerical equation you derived, the algebraic equation you derived, is consistent with the differential equation that you started with. Okay, that when you go to delta small grids, the two would lead to the same equation. Okay, that doesn't always happen. That is the problem of consistency, right? Because we have a differential equation and we are trying to turn it into algebraic equations, right?
Yes.
We do it through a process. During that process, we can say the phi is linear, or we can say it's a parabolic function. We can say it's an exponential function, right? And we will derive algebraic equation. Okay.
Yes,
now, okay. So during the process, if we do not have a good handle on the boundary conditions or initial conditions or the distribution, you can derive a equation which is not consistent anymore. Okay, with the basic physics. It's the concept of the physics, right? Stability, on the other hand, depends upon, you could have a scheme which is consistent, but there is a stability problem, because like in the case of central differences, for example, central differences give you an equation which is consistent with the differential equations. But now if you do a central difference for a grid number, a grid Peclet number which is higher than 2, your coefficient becomes negative. That coefficient implies convection is not impacted, but that coefficient implies that the flow can go, or the temperature can go from a lower gradient to a higher gradient. A negative coefficient basically means that. Negative coefficient means that the numerical code is trying to send heat flux or from a lower pressure area, lower temperature area to a higher pressure temperature area, which physically doesn't happen. Okay, so the scheme becomes inconsistent. Scheme becomes unstable. Okay.
Yeah. Okay, sir. Thank you.
Okay, I think we'll thank once again Dr. Runchal, and I'll request Dr. Dalal to proceed with his presentation. Professor Dalal, please.
Hello, good morning. So thank you, Dr. Sumer, for inviting me to give this lecture, and I will be talking about this finite volume method. And let me first share the presentation. Is it visible?
Yeah, absolutely. Just please move that stop sharing bar little. Yeah. You have stopped your presentation.
Is it visible now?
Yeah.
Okay.
Not visible now. Yeah, it's fine. Yeah, now fine.
Okay. Thank you.
Yeah, please.
So in today's lecture, first I will touch upon this finite volume method for discretizing convective diffusion equation, and already Dr. Runchal have introduced it, but just I will go through this mathematical derivation in steady state two-dimensional situation, and then we'll discuss about unsteady convective diffusive equation, how to discretize it, that mathematical derivation will carry out. Then finally we'll consider the steady state Navier-Stokes equation, and this Patankar's famous simple algorithm we'll discuss to discretize this steady state Navier-Stokes equations, and at the last we'll discuss about the boundary conditions. So as Dr. Runchal told that based on this conservation's law and with certain assumptions, we can write down the governing equations for fluid flow and heat transfer. So you can see that mostly I will discuss about the incompressible flow, and we'll consider laminar flow. So these are the governing equations in differential form. So first one is continuity equation, and this is the general transport equation where pi is any general variable. So we can represent any equation in this form. Even you can see that x momentum equation. If you replace pi with u, small u, where u is the velocity in x direction, then we can write the x momentum equation with a pressure gradient term. Okay, so minus del p by del x, and we can have some other source term. And similarly, if we replace pi with the enthalpy h, then energy equation in terms of enthalpy, we can write it like this. And if we have a species transport equation, then if we replace with mass fraction yi, then we can write down these transport equations. So all you can see that these equations we can write in this general transport equation, and we actually these are partial differential equations. Now using some suitable discretization technique, we convert it into algebraic equations, and those equations we need to solve inside the domain. So we need initial conditions if it is an unsteady problem to solve these equations, and you can see that at time t is equal to 0, either we need to give the constant value, or it may be spatially varying value. And boundary condition may be three different types. One is Dirichlet, where we prescribe the value at the surface. So phi, maybe it is constant, or it is spatially varying, or it may be varying with time and space. And we can have Neumann type boundary condition. That means we prescribe the flux at the boundary. So normal to that surface, we del phi by del x, we prescribe it may be 0. So if it is called for heat transfer, if it is a adiabatic condition, then there will be no heat flux across the surface, then obviously we normal to the surface, then this will be 0. And we can have Robin or mixed type boundary condition. So we generally it is a linear combination of this Dirichlet and Neumann. So we can represent as alpha phi plus beta del phi by del x is equal to gamma, where alpha, beta, gamma are the coefficients. In general, so already Dr. Runchal discussed that we can have three different types of discretization techniques. Finite difference method, where we use Taylor series expansion and the derivative we write in terms of the nodal value. And in finite volume method and finite element method, we integrate the equation over a control volume. So that is the difference with finite difference method. So here mostly we'll discuss about the finite volume method. Now we have the governing equations, and using some discretization technique, we'll convert this partial differential equation to some algebraic equation, but we need to solve at some point, right? So for that, we need to divide the domain into grid, and this grid may be two types, structured grid and unstructured grid. So in structured grid, you can see that it has regular connectivity, and you can actually represent the neighbors with some indices I, J, K in 3 dimensions. But whereas in unstructured grid, it has irregular connectivity, and it is very difficult to index the neighbors with means with I or I, J, K. So generally we index with the cell number in unstructured grid. In structured grid, obviously, if you consider at any interior point, it will have equal number of neighbors. But when we consider unstructured grid, so it is very, it may not have equal number of neighbors. So if you consider very complex geometry, then mostly we use unstructured grid. So you can see in the commercial softwares, they use unstructured grid so that it is easier to generate the grid in complex geometry. So at each grid point, we need to solve this algebraic or discretized equation. Now we can have in structured grid, we can have a regular grid, like the grid follows the in Cartesian grid. So these are orthogonal, you can see. In cylindrical grid, so these are orthogonal, and in spherical grid, these are orthogonal. So these are known as orthogonal grid. Whereas in block structured grids, if you have a complex geometry, then we divide the domain, and in each block or each zone, we generate the grid, and at the interface we make the continuity. So for complex geometry, we can generate the structured grid using these zones or blocks. Whereas in curvilinear grid, we use some algebraic method or elliptic method, so that the grids actually follow the boundary. So this is known as also body fitted grid, and you can see that each domain, these grids are actually following the boundary. So these are examples of structured grid. And in unstructured grid, we can have regular grid or hybrid grid. So you can see this is unstructured grid, triangular mesh. And in hybrid grid, there are more than one type of cells will be there. So if it is a 2 dimensions, then we can have quadrilateral mesh or triangle mesh. So near to the boundary, obviously boundary layer forms. So it is better to have structured orthogonal grid near to the high gradient region. So you know that near to the wall, velocity varies from 0 to some value. So obviously high gradients appears near to the boundary. For that reason, it is better to have structured grid or boundary layer grid. And away from the surface, you can have this triangular mesh. So you can have if you use unstructured grid, so obviously you can have the advantage of local refinement. So you can see here we have very fine mesh. And in 3D, we can have these different types of grid, but nowadays in commercial software, you can have any polyhedra. So in grid terminology, so we can have that when we use a finite difference method, generally we discretize these equations at the node or vertex. But when we use finite volume method, generally we integrate over a cell, and this is known as cell centroid. And these are the faces, and the face, this is known as face center. So center of the face. So first we'll discretize the steady diffusion equations. Then I will know that how to discretize the diffusion equation. Then we'll consider convective diffusive equation. So you can see that this is the grid in the finite volume method. Instead of this indices ij, we will represent with this node P. P is the capital P is the cell center of the main control volume, and capital E, which is representation of the neighbor cell center east. Okay, this is the west, north, and south. So these are the neighbor cells, and you can see in this volume, these are the faces, and the face centers are denoted by small e, small n, small w, and small s. So these are east, north, west, and south. These are the face centers, and these are the grid spacing delta x and delta y, and the distance between two cell centers. These are delta x e is the this east face, and this is a delta x w. Similarly, delta yn, and delta ys. So we can have this steady diffusion equation in vector form. We can write where gamma is the diffusion coefficient and s is the source term, and phi is any general variable. So we can write flux vector as j is equal to minus gamma grad phi. So this, if we write it here, so we can write divergence of j is equal to s. So now this equation we need to integrate over this control volume. So in the main control volume, so if you integrate it over this main control volume and use the Gauss divergence theorem, then you can convert this volume integral to surface integral. Now you are writing in terms of fluxes. Okay, so surface fluxes. So we now one approximation or assumptions we make here, that this j, now you need to integrate over these surfaces, right? So in 2 dimension here we are showing here, but if it is a 3 dimension, then it will be a surface, 2-dimensional surface. So over that surface you need to integrate. So now we'll assume that j varies linearly over these each of the face, so that it may be represented by its value of the face centroid. So face centroid is small e, small n, small w, small s. So we'll represent this j as the value of this cell face centroid. So obviously you can see this integral now we can write as the face centroid je dot ac, and we have 4 faces in this particular quadrilateral cells. So we can write in this form. And in the right hand side, whatever we are integrating over the control volume, this source term, now we will assume that this source term average value lies at the cell center P. So that is the S bar value. This is the average value at the cell center. So we can write S bar delta V, where delta V in this case it is delta X and delta Y, and these are the surface vectors at the east, west, north, and south faces. So obviously you can see that east faces, this surface we can vector, we can write AE, I, where I is the unit normal in the x direction, and obviously you can see this AE is equivalent to delta y, so it is equal to delta y. So AE and AW are delta y, and AN and AS is the delta x. So now you can see that we always consider that normal outward normal from the face. Okay, so if it is outward normal, then when we consider the west face, obviously it becomes minus AWI, because here normal is opposite to the x direction, so that's why it becomes minus AW. And when we consider south space, it will be minus ASJ, where J is the unit vector in y direction, but as normal on the south face is negative to the y direction, so it will become minus. So obviously now first let us find what is JE dot AC, then similarly we can find the other phase fluxes. So when we consider JE dot AC, so obviously you can see that this quantity is J, so that at east face we need to consider, and with a dot product of this surface AC, where AC is nothing but AE I. Okay, I is the unit normal in the x direction. So now we can see that we can use this that piecewise linear, what Dr. Runchal told, that the value varies between the cell centers in piecewise linear manner. So we can actually calculate this grad phi dot I as del phi by del x. So JE dot AC we can write minus gamma E AE phi E minus phi P. So where del phi by del x, which is the gradient at east face, so that now using Taylor series you can write the phi E minus phi P divided by the distance, and this is delta XE. So now JE dot AC we have written this way, and this gamma E AE divided by delta XE we will write with a coefficient DE, so we can write minus DE phi E minus phi P. So similarly for other phases we can represent in this way. Now if you put it in this equation, all these terms, then we'll get finally this equation, and where this D plus DW plus DN plus DS we write as the coefficient of this phi P, so that will represent at AP, so it is AP phi P. And in the right hand side, now you can see this we have, so these we can write as summation of all the neighbors A and B phi and B, where A and B is the coefficients, and we have the source term is bar delta B, so that we are representing as B. So in finite volume method, here we are writing AP phi P is equal to summation of all the neighbor A and B phi and B plus B. Now this actually P is the representation of Ij, and east, west, north, south, these are I plus 1j, I minus 1j, Ij plus 1, and Ij minus 1. So this is the discretized equation, and this you need to solve at each grid point. So now we have learned how to discretize the diffusion equation. Now let us add the convection term. So if we add the convection term, so you can see this is the in 2 dimension, this is the equation, and this equation is linear if velocities are known, and we are solving for phi. So if you are solving for phi, then this is the representation in vector form, and this if you take in the left hand side, then you can write divergence of rho u phi minus gamma grad phi is equal to S. So now you can see this we can write as a flux vector. Here this flux vector contains both this convection flux as well as the diffusion flux. So this divergence of J is equal to S, already we have learned how to discretize using finite volume method, and what are the approximation involved while discretizing using finite volume method. So now this is the representation of the discretized equation. Now each term we need to evaluate, because now we have the additional convection term. So now JE dot AC, if we represent, now we have this rho u phi minus gamma grad phi. So gamma grad phi already we know that how we have discretized with, but here rho u phi we have to consider. So now rho u phi dot AEI, because this is the surface vector AC. So this will give actually if you make this u is velocity vector ui plus vj. So if you make a dot product with AC, then you will get only small u, which is the velocity in x direction. So this rho u phi e ae, e means the at the east face, and minus gamma grad del phi by del x at east face ae. So this already we know how we have discretized, and it is minus de phi e minus phi p. But here now you can see that we have this phi at east face, and we have rho ua, and rho ua is nothing but the mass flux at the east face, right? So that we are representing as mass flow rate Fe phi e, because we have rho, so rho uae, so that is your mass flow rate Fe, so Fe into phi. So now you can see that when we are actually discretizing this equation at cell center P, so obviously the value at small e or the phase centers, those are unknown. Now how do you calculate that? So one simple way that you make a average at this point. So this ue, you are taking ue plus up divided by 2, so that it is average, so it is a central difference kind of thing. And now what about this phi p, phi e? So phi is also unknown, and we are solving for phi, right? So this will use some convection scheme. So here AP is known as convective coefficient, and phi is the convected variable. So that means due to this flow A, actually phi is convected, and this phi is the convected variable at the east. Sound is coming. Yes. So this is the convective coefficient. So depending on this value, actually whether it is positive or negative, we can use different upwind schemes, and the or simple way we can use the central difference scheme. So and we have higher order schemes like third order upwind scheme you can use like quick. So this now let us see that how we'll use it. So if you use central difference scheme, then we can represent phi e as phi e plus phi p divided by 2 for uniform grid. So now we know that how we have discretized Je dot AC. So this is the discretization equation where AP is the mass flow rate using convection scheme. But if you using the central difference scheme, but if you use other schemes like first order upwind or second order upwind or quick, so this term will be different. Now, similar way, you can discretize, you can calculate JW dot SW, JN dot SN, and JS dot SS. So all these you just put it here and simplify it, then you will get the equation as these are the coefficients for the phi p, and all these coefficients of neighbors phi e, phi w, phi n, phi s you take in the right hand side, and you can write this AP. So AP we can write as this coefficient, but you can see that if the east coefficient AE D minus AP by 2, so this we can write as D minus AP by 2, and as we have subtracted 1 minus AP by 2, we are adding 1 plus AP by 2, and we have another AP by 2. So these two AP by 2 will give AP. So you can see that all these summations we can write as AE plus AW plus AN plus AS, and this will give AP. Similarly, we will get minus FW plus FN minus FS. So you can see that AP, which is the diagonal coefficient, it is summation of all the neighbor coefficient plus summation of FF, which is the net outflow from the phase. Okay, AP minus FW plus FN minus FS. So you can see that when at convergence, obviously the continuity equation will be satisfied. So this term will become 0. So you can see that we can represent finally in this AP phi p form. So AP phi p is equal to summation of ANB phi NB plus B, where all this coefficient AP is summation of all the neighbor plus summation of FF, and AE, AW, NS are represented by this. So now we have learned how to discretize the convective diffusive equation. But now if we add the unsteady term, then let us see that we need to integrate how to integrate over the time as well. So we need to integrate over time as well as over control volume. So you can see that we consider the unsteady convective diffusive equation. So this is in the vector form we have written, where we have del rho phi by del t. So similar way, this we can represent as a flux vector, and this is the representation. Now this equation we need to integrate over this control volume and as well as over the time. So you can see now we can now integrate all these terms over control volume as well as over the time. So we are going from Tn to Tn plus 1, where Tn is the previous time and Tn plus 1 is the current time or present time level, and that difference between this time is the time step, and that is delta t. So now first you can see that this term, if we use that it is non-deforming control volume, then we can take del of del t outside the integral, and we can write this first term as d of dt of rho phi p delta p. So this we have written, and this term already we know how to discretize, right, over the control volume. That we have represented as summation of ff jf dot sf, where f is small e, small w, small n, and small s. And we are integrating over time also, so we have dt and the source term. So now you can see that when we are integrating these equations over the time from Tn to Tn plus 1, so at each time we need to know the value, but it is not possible, right? So either we have to take the value from Tn or Tn plus 1. So now we'll take some average value at time level tau, and we are writing that this all these terms at a time level tau, where tau in between Tn and Tn plus 1. So you can write, so this you can see that we can write rho delta b. Rho, as in incompressible flow, it is constant. Delta b, I told that it is non-deforming control volume, so delta b you can take it outside, so it will get phi p n plus 1 minus phi p n, where n is the previous time level and n plus 1 is the current time level. And all these values, whatever these fluxes we need to find at a time level tau, and this source term also we need to find at time level tau. So now how to find tau? So obviously, as I told, that we have the values available at Tn or Tn plus 1. So so now you can see that we'll just write this term, whatever we have discretized and we have written in terms of tau, as a factor of this jf sf jf dot sf tau. We'll write ft, the fluxes at n plus 1 time level, plus 1 minus ft, the fluxes at time level n. So now we are just writing this with a factor ft, where ft varies between 0 and 1, and you can see that we are writing ft times the fluxes at time level n plus 1 and plus 1 minus ft into the fluxes at time level n. So where n is the previous time level and n plus 1 is the current time level. And similarly, we are writing this source term with ft times the source term at n plus 1 time level and 1 minus ft times into this source term at nth time level, because we have the values available either at n or n plus 1. So we are writing with a factor. So now if you write all these terms, summation of jf dot sf using central difference method, you can see that already we have discretized and we know all these terms, and if you just rearrange these terms, you will get this term. Okay, and if you put it in ap phi p form, so we can write ap naught, where ap naught is rho delta b by delta t, plus ft into summation of nb plus summation of ff, where summation of ff is the net outflow from the flux from the surface, outward flow, net outflow from the surface. So that means at convergence it becomes 0, and we are writing phi p n plus 1. So n plus 1 we have taken in the left hand side, all terms we have taken in the right hand side. Summation of nb ft phi nb n plus 1 plus 1 minus ft phi nb n, and ap naught minus 1 minus ft whole means in bracket summation of A and B plus summation of FF phi P at N and plus B. So where so AP is AP naught plus FT summation of NB plus summation of FF. AP naught is rho delta B by delta T, and B is this one. So now you can see that this we have written with a factor FT. Now if FT becomes 0, what will happen? So if FT becomes 0, then you can see that we will have only one unknown term at phi P n plus 1, and all the other terms will be known from the previous time level n. So we are putting FT is equal to 0 in this discretized equation, then we are getting actually explicit scheme. So because only one unknown is there, so this is known as explicit method. So you can see that obviously in the right hand side all the terms are known, so you can just find the phi P at n plus 1. But when you put ft is equal to 1, then we will have more than one unknown at n plus 1 time level. So you can see that if you put ft is equal to 1 in earlier expression, then we will get ap phi p n plus 1 is equal to summation of nb phi nb n plus 1 plus ap naught phi p n plus b. So you can see that all the neighbor terms are unknown, right? Because at n plus 1 time level we are trying to find what are the values, so obviously those are unknown. So this is known as implicit scheme, because we have more than one unknowns. So and these two are actually if you see in it is second order accurate in time, sorry, first order accurate in time, okay, both explicit and implicit. But if you put ft is equal to half, then it becomes Crank-Nicholson method, okay, Crank-Nicholson scheme. So if you put ft is equal to half, then you will get ap phi p n plus 1 is equal to half summation of nb phi nb n plus 1 plus phi nb n. So n and n plus 1. So and with phi pn, this is the coefficient. So you can see that this becomes second order accurate in time. Okay, so this scheme, and we have already used diffusion discretization second order, and also the convective scheme whatever we have discretized using central difference, so that is also second order. So when we use Crank-Nicholson method, obviously it is overall second order accurate. Now we have learned how to discretize the convection diffusion equation. Now quickly we'll go in discretizing the Navier-Stokes equation. So you can see that this is the steady Navier-Stokes equations, and when we discretize this equation actually in the main control volume, then using this grid which is known as collocated grid. What do you mean by collocated grid? Collocated grid means all the variables we stored at the same location. Okay, so at cell center P we stored all velocities u, v, w, pressure, and any scalar like temperature or the mass fraction or species. So if you discretize the pressure gradient term here, so we can write this minus grad P like this, and if you integrate it over this control volume, then you will get minus summation of PF. Okay, so and for u velocity it is del p by del x, so it will be just for the I direction, that means it will be in the wherever whatever the velocity direction is there, that we need to consider in this I. So when we consider x momentum equation, then obviously it will be in the direction of x. So you can see that for x momentum equation, if we discretize this pressure gradient term, then we will get minus p minus pw delta y. Now you see, when we are using collocated grid, obviously the pressure is known only at the cell center like capital P, capital E, capital W, capital N, and capital A. So obviously at the phase center, if you want to find, then we have to take some average. So if we take the average, then you can see that it will become P minus PW. So we write P plus PP divided by 2 and minus PP plus PW by 2. So we'll get minus minus P minus PW delta Y by 2. And similarly for the V equation, if we write, then it will be minus Pn plus minus PS delta X by 2. Now see here. So if you are using collocated grid, so we are actually, when we are solving the governing equation at this cell center P, we are using the pressure far away point, right? Because we are using pressure at east and this west. So you can see that it is like we are using this pressure from the coarser mesh. Okay, one thing. And second thing is that although we are solving the momentum equation in the main control volume, any pressure from that main control volume is not involved. Okay, so that is the problem. And if we have some wavy pressure field, then we will see that it will become 0. So if you have a zigzag pressure field, let us say due to some oscillating pressure field, we have the zigzag pressure field like 100, 200, 100, 200, and at east and west we will get 150 and 150 and sudden and if you see in the previous equation, so this will become 0. If this becomes 0, that means velocity and pressure will decouple, because in the you can see that velocity u will is due to the pressure gradient del p by del x, but pressure gradient is becoming 0, so that means velocity and pressure will be decoupled. So that is the problem in using collocated grid. So for that we can use staggered grid. What is staggered grid? So in the staggered grid you can see that pressure and any scalar will be stored at the cell center, and velocities will be stored in the staggered way. So these are the pressure or any temperature species will be solved in the cell center, and this is velocity u and this is the velocity v. So if you use this way, then pressure and velocity decoupling can be avoided. So similar way you can discretize the continuity equation and you will get this. And here also you can see that when you are solving this continuity equation in this main control volume, it is not taking the velocity from that that volume. So for that reason, actually Patankar proposed this simple algorithm where simple is used for introducing pressure into the continuity equation, and we can write one pressure correction equation. So you can see this is the main control volume where we solve for pressure and any other scalars, and velocities we solve in the staggered way. So this is the main control volume for the u velocity, and this is the main control volume for the v velocity. Okay, so here just we have represented red color. So this is the u control volume, this is the v control volume, and this is the main control volume. So you can see now when you are solving this pressure continuity equation in this main control volume, actually you are using the velocities from the phase center where you are solving the velocities. So you don't need to interpolate the velocities at the phase center. Okay, and when you are actually satisfying the continuity when you are solving for u momentum equation here in this control volume, you are taking the pressure from the phase center p minus pp. So there you don't need to take the average at the phase center. So you are taking the actual value. So pressure and velocities are not decoupled in this way in the staggered grid. So this simple stands for semi-implicit method for pressure linked equation proposed by Patankar, and it is used this like means ANSYS Fluent software and any other commercial software. And now let us write down the discretized equation, because we have already discretized for steady state convective diffusive equation. So for this small e phase, although phase center for the main control volume, but it is the cell center for the u momentum equation, and this is the cell center for the v momentum equation. So these are the discretized continuity equation. Now you can see to solve this equation you need to know the pressure, but we don't know the pressure when we are starting the solution. So let us guess a pressure. Okay, so if pressure is guessed as p star, then we can solve this equation. And if we solve this equation, obviously this velocity is not a correct velocity, that is known as provisional velocity, right? Because pressure we have guessed. So with p star, if we guess the pressure, we'll get some provisional velocity u star. Okay, so now we are writing these equations with the known means guessed pressure value and with the provisional velocity. So now these equations, if we subtract, okay, subtract equation 2 from equation 1, then we can write down like this. Now here we propose a correction to the start velocity UE prime such that it will become the original velocity UE. So which will satisfy the continuity equation. So UE is equal to UE star plus UE prime. So obviously you can write UE minus UE star is equal to UE prime, and similarly Bn minus Bn star is equal to Bn prime, and P minus P star is equal to P prime. So these if we invoke here, then we will get the equation like this. So these are known as velocity correction, okay, equation. So UE prime and Bn prime. And now we can see that this equation, this term, summation of A and B, U and B prime. So now at the neighbors also you need to know what is the correction of this velocity. So, and this will also involve the other neighbors correction velocity. So obviously it is very cumbersome to calculate. So Patankar proposed that if you drop this term, finally there will be no change in the solution, because this is the velocity correction only, okay. And as you are dropping this term, so it is no longer full implicit, okay, because it will have the effect in the pressure correction equation, okay. So for that reason it is known as semi implicit, okay. So in a simple algorithm it is written that semi implicit. So now when we use simple algorithm, we drop this term and it becomes very simple. Then this velocity correction we can write in terms of the pressure correction values, right? So UE prime, Bn prime, and similarly for west phase and south phase you can write Bw prime and Bs prime with the coefficient Dn, D, Dn, Dw and Ds, which are represented like this. So now if we consider the continuity equation, and now your continuity equation we need to satisfy in the main control volume, right, at P. So that we are integrating over this control volume, use Gauss divergence theorem to convert this volume integral to surface integral, and this is the equation. So now FE, FW, Fn, Fs, these are the mass flow rate at east, west, north and south phase. We can write like this. Now we have the start velocity or this gas provisional velocity. So with provisional velocity if we calculate, then these are the provisional mass flow rate. And also we know Ap is equal to Fe star plus Fe prime, because we know that U E is equal to U star plus U prime. So with that we can write this corrected phase flow rates, and that if we put in this equation, then we will get F prime, Fw prime, Fn prime, Fs prime like this. And if you put it here, we'll get the equation for pressure correction. So you can see, you can write Ap Pp prime is equal to summation of Anb Pnb prime plus B, where B is nothing but the minus of net outflow of the mass flow rate from the phase. So this is known as pressure correction equation. So now you can see that invoking the continuity equation from the velocity correction, we have written this we have derived this pressure correction equation. Once you know the pressure correction, then you can know the velocity correction, and if you know the correction, then obviously with the whatever provisional velocities you have got, so if you correct it, then you will get the correct velocity field. So now let us see the simple algorithm. So we are guessing the pressure, okay. So P star, then with that you solve this equation and find the provisional velocities, and then you calculate the summation of Ff star with this known provisional velocities. Then you solve this pressure correction equation, whatever we have derived. Once you know the pressure correction, then you know the velocity correction, and velocity correction once you know, then you can calculate UVP, okay. And now you see the check for the convergence. If it is not converged, then again you repeat it. So in this case we have dropped this term summation of A and B, U and B prime, right? So those we have dropped. So for that it is prone to diverge. This pressure correction equation is prone to diverge. For that we need to under relax it. So you can use P is equal to P star plus some under relaxation factor into P prime, okay. This under relaxation factor you can actually vary depending on maximum value you should take, but in trial and error method you need to find the value. Mostly it is used in ANSYS fluent between 0.6 and 0.8. Now there are families of these algorithms, simple algorithms. One is like simple revised. Here what we did, that whatever pressure we guessed, and based on that we got the provisional velocity. So instead of that, it is proposed that you find some good pressure field. If you get a good pressure field, obviously it will converge fast. So for that reason, these equations are written like this: UE is equal to this divided by AE, which is represented as UE hat, and VN is equal to VN hat plus this pressure term. So now all these, if you put like this, and if you in the discretized continuity equation, if you put, you will get a pressure equation. Okay, pressure equation. So if you put it here, you can see that you will get a pressure equation like this. Okay, so if you solve this pressure equation, then you will get a good pressure field, and that now you use in the simple algorithm as a guessed value. Okay, so obviously you can see that you are giving a good guess value of the pressure. So in this case, simpler algorithm, you can see, although you are solving one additional equation for pressure, but it converges faster than the simple algorithm, because you are giving a very good pressure field. So in the simpler algorithm, you can see that we are first we guess the velocity field, then calculate the FF hat, then we solve for pressure correction, pressure equation. Once you know the pressure equation, so that is the guess value, and you solve the provisional velocities, calculate the provisional mass flux, then solve for pressure correction equation P prime. Once you know the P prime, you can calculate the velocity correction, and you find the velocities. But here do not correct the pressure, because we have already solved the pressure, and check for the convergence, then repeat. Then another family is that simplex, simple corrected, right? So if you remember that when we wrote this correction equation, velocity correction equation, we drop these terms in the simple algorithm. So here it is proposed that you don't drop this term. You write this summation of A and B, U and B prime as UE prime summation of A and B. So UE prime already it is in the left hand side, for which you are actually finding. So this UE prime, if you put it here, you are getting that UE prime and Bn prime like this. Okay, so here earlier it was delta y by AE, but now you have delta y by AE minus summation of A and B. So if you put these if you make these changes, then obviously you can see that you are not fully dropping this term. So it is actually, it converges faster than simple algorithm. So it is the same algorithm is followed. So guess the pressure field, solve for U star V star, which are the provisional velocities, calculated the FF star, then you solve for pressure correction equation, then from pressure correction equation you find the velocity correction, and once you know the velocity correction, you find the pressure and velocities. So then you just check for convergence. Now we are solving for velocities as well as pressure correction. So we need to know the what are the boundary conditions. So obviously you can see that for either we can give the normal velocity at the boundary, or we can give the pressure field. Okay, so generally if it is a inlet, so obviously we give some velocity field or mass flow rate, and at the solid wall we give no slip conditions. That means velocities are 0, and at outflow generally we use the in velocity directions, we know we gradient we make 0, del u by del x is 0, del v by del x is 0. So these are the velocity boundary conditions. And now what about the pressure correction boundary condition? Now you have seen that we have represented Fe prime is equal to minus rho e d delta y p prime minus pp prime, right? So here you can see that if we know the velocities, okay, so if you know the velocities, okay, so say let us say this is the boundary, this is the boundary, and this is the control volume. Here P is the cell center. Now for this boundary we can write FB prime is equal to minus rho b dB delta y PP prime minus PB prime. Okay, and now the FB you can write FB star plus FB prime, but as velocity is known, right? If velocity is known at the boundary, then if velocity is known at the boundary, then obviously FB star is known, because you know the mass flow rate, right? If you know the mass flow rate, then this correction will be 0. FB prime will be 0. So FB prime is 0. That means for this boundary, you can see PB prime minus PB prime is PP prime minus PB prime will be 0. That means del P prime by del X, because X is in these directions. That means del P by del N will be 0. Del P prime by del N will be 0. That means if velocity is specified at any boundary, you need to give the normal gradient as 0 for the pressure correction. Okay, so if velocity is specified at any boundary, the pressure correction boundary condition will be that normal gradient of pressure correction will be 0. And if pressure is known, then pressure correction should be 0, right? So that means if pressure is known, then obviously if pressure is known, that means you don't have any pressure correction, so PB prime will be 0. So now I think we have come to the end. So if you have any questions, let us discuss.
Hello, good morning, Professor Dalal.
Good morning.
Myself Prashant, I am from NPCI. So, what I could understand that if we are using simpler and simpler algorithms, we should get the same solution, because finally it will depend on the convergence of pressure or mass.
Yes.
But the time will only vary.
Yes, the solution time will vary.
So will it be dependent on grid to use some specific type of algorithm, or generally if some fast algorithm, what will be your suggestion?
Say it doesn't depend on the grid. Okay, so it depends. You can see that when we are using simpler algorithm, we are solving one additional equation, right, for the pressure. So obviously it will take more time to solve the equation, but as you are giving a correct pressure field or more good pressure field, it will converge fast. But it depends on that how you are actually say in the simple algorithm, if you can give a good pressure field, say instead of giving a 0 pressure field, or if you give some other pressure field, then obviously simple algorithm may converge faster than the simpler algorithm. It depends on that how you are giving the guess value of the pressure field. And similar way, simplex, just only simple some difference is there. So simplex will be obviously faster than the simple algorithm, but we cannot give any specific direction that which one will give you faster result. It depends on that how good initial value you are giving, or guess value of velocity field or the pressure field you are giving.
Okay.
But mostly in the commercial software, you can see that simple algorithm is given, but it depends on how you are giving a good guess field of the velocities and the pressure. Thank you.
Because ultimately they are looking for the convergence, so it will have the convergence in all the cases. So only time will be the matter of interest.
Yes, yes, yes.
Yeah, you may please ask the questions. Any doubts? I was seeing some comments from Deepak Kumar. Deepak Kumar, are you there? You can ask some of the doubts you had.
Sir, good morning, sir.
Good morning.
Sir, is there any commercial application with the collocated grids?
Yes, yes. Say you can actually overcome this velocity pressure decoupling using momentum interpolation. There is a method, and mostly say when you use unstructured grid or commercial software, they use collocated grid formulation. Okay, because it is easy, because you can see in the staggered grid problem is that you will have different grids for different variables, and it is very difficult to bookkeeping. So for that, collocated grid is mostly used, and you need to overcome this velocity pressure decoupling using momentum interpolation. So due to Ri and Chow, it is actually proposed by Ri and Chow, and that if you use, then you can use collocated grid.
So it means momentum interpolation has only application with the collocated grids, not with the staggered grids and all.
No, it is not required.
Okay.
Thank you.
Dalalji, whatsoever the algorithm you have shown, what I could understand, please correct me if I'm wrong.
Yes.
While we are calculating the momentum term, we have to utilize the central difference method, that is summation of the velocities from the two cells and then divide by 2. But when we are using the convective variable,
Yes.
we have to apply the convection like first order of wind or second order of wind.
Yes.
Okay.
We still have 3 minutes left. Anybody wants to interact? Professor Dalal will be happy to discuss.
Sir, will there be any limitation with respect to Peclet number and Quorum number for this grid? There will be something, Peclet number should be less than 2 or Quorum number should be less
Yes,
than
as Professor Dr. Runchal discussed. So obviously that will be also, he showed for one-dimensional grid. So it is also applicable here. But CFL condition will not come here because we are not treating with the unsteady term, because we discretize only steady state Navier-Stokes equations. CFL criteria will come in choosing the time step delta t, right? Then the it is the stability criteria. So as we discussed in the simple algorithm, using simple algorithm, the steady state equation, so CFL criteria will not come.
So generally it is advisable to keep Peclet number below 2 and CFL value below 0.1. So these are the thumb rule we can say.
No, CFL, that's why I'm telling, CFL number will not come here because we discretize the steady state equation, right? But Peclet number, whatever Dr. Runchal told, say if you are using first order upwind or central difference, so accordingly you can use some hybrid scheme so that automatically it will switch on whether it is central difference or first order upwind.
Okay.
Any other questions?
Maybe I think you can discuss for a minute about pressure velocity, that decoupling. Just how pressure and velocity can get decoupled and like that.
So yes. So that I told that say when we use collocated grid, we are discretizing the momentum equation and the continuity equation in the same grid point. So we have shown that if you are using that, then the values at the faces will come for the pressure gradient, right? When you are discretizing del P by del X or del P by del Y in the X or Y momentum equation, we have seen that it actually contains the value at the face center, but face center now it is not the value is not available, so we need to interpolate in some way. So we use, if you use central difference scheme, then we can make that it will be the PP plus PE divided by 2 for del P by del X at east face, and similarly you can see that west face, then it will become PE minus PW, where these are not actually containing the value of the main control volume, right, pressure. But although this pressure, the driving force is the pressure gradient, right? But we are not getting that pressure from the main contour balloon. So that is one of the problem. Other problem is that when we are actually if we have some pressure field which are say oscillating pressure field like 200, 100. So in some situation where you have a means a pulsating flow, then your pressure may vary or oscillate like this. So in that case, you can see that your pressures all pressure gradient will become zero, although there is a oscillating pressure field, but momentum equation will feel that it doesn't have any pressure gradient. Okay, so obviously if there is no pressure gradient, there will be no flow, right? Because pressure gradient is the driving force for the velocity. So that is the problem, and that is known as pressure and velocity decoupling, because now pressure gradient is becoming zero and pressure and velocity will not talk each other. Okay, so to overcome that problem, we are using this staggered grid. But as one of the participant asked, that we can also use collocated grid, but we need to use momentum interpolation, and there we separately actually this pressure and velocity we couple, okay, using momentum interpolation. Sumedh.
Yeah, thanks. So we'll move on to the next speaker. Dr. Murali Damodaran, can you start?
I'm
Hello.
Yeah.
Nice to
Hi.
see you.
Okay, let me try to share my screen, and we will take from there. Are you able to see anything?
Yeah, we are able to see. Please press F5
No.
so that it will be a full screen. Yeah. Excellent.
Are you able to see the entire screen?
Yeah, wonderful.
Okay, welcome everybody. I think you must be getting tired and hungry, so I try not to, bore you with a lot of mathematical details. But the theme I've been asked to talk about is the finite volume methods for compressible flow. I have many years of experience in this field, and I've also used this method for incompressible flows as well. So the focus of the flow field that I will be interested in talking about today is in the subsonic, transonic, and supersonic flow regime. That is between the Mach numbers of 0.8 and 2.0. So what you see in this characteristic is the presence of discontinuities, such as the shock wave, expansion waves, and then of course there is the boundary layer. And the Reynolds number for such flows are always very large. So the boundary layers tend to be thin, but it can be separate and things like that, depending on the pressure gradient in the direction of the flow. Flows are also computed inside high-speed nozzle. For nozzle designs, we want to see the presence of the shocks like this. You can see complex structures and expansion waves and things like that. This is all solving the full Navier-Stokes equation by finite volume methods, and that is what so I begin with reviewing the compressible flow models, because there are a wide variety of such flow models. So one is the integral form of the unsteady compressible Navier-Stokes equation. You have the flow variables, conservative variables here are the density, the momentum in the 3 direction, and the energy. The form of this flux vectors you see takes this form. As this video is being recorded, you can always look at the details in greater detail. The shear stresses and all that takes this form. Here you can see some terms with the viscosity in terms of the T here, mu T, that is the eddy viscosity. And for that, you need to do some turbulence modeling. So there are a wide variety of turbulence models, and I believe this afternoon Dr. Madhukar will be talking to you about those things. So those things will be fit inside here, RANS and LES models. For a direct numerical simulation, you don't need to model the turbulence. You will just solve the Navier-Stokes as it is. But the computational resources for that are terribly huge. And because of the limit on the resources available to different research groups, the problems they can solve with DNS is very limited. Okay. So the differential form will come from the integral form, and you can take a transformation and you can get the differential equations. This you can see in any elementary fluid dynamics text. It is always a good practice to do some scaling. Most of the students and researchers working in the industries, I see that they are not using that most of the time, because they may need the value right away. But scaling has its advantages, especially when you want to train machine language surrogates with the data. It will be good if you train them with scaled data. So I've introduced a slide here showing the form of scaling that is used in the open source software SU2 and what I'm familiar with. So here you can look at it at your own sweet time. If you use this scaling parameters and non-dimensionalize your equations, you will get the form which looks exactly like the dimensional form. Of course, with the Reynolds number and all that, viscosity all will turn into Reynolds number and various other. So if I look at a mesh, for solving these equations using finite volume, I need a mesh, and most of the time we use body-fitted mesh or hybrids with structured mesh near the complex airfoil shape or aerodynamic configuration. So if I don't use scaling, then I have to actually put the actual values of the flow field. Say this is the incoming velocity, it's say 200 meters per second. But if I scale it, then the corresponding thing.
Sorry to interrupt. Are you having another slides, or just because we are able to see only one slide, written compressible flow models?
No, I'm showing other slides, so I don't know why.
Slides are not moving, sir.
Oh, I don't know. Wait a minute. You're not able to see the compressible flow models? How about now?
No. Slides were not moving. That is what.
I don't know how to get it. Wait, let me try.
You'll have to manually click on.
No, I'm trying to. You see, I did something different here. I have a 12 slide overarching, and then I link to other slides. Okay, I don't put everything in a single slide, but it shouldn't matter. It should move, because what you're seeing is on the screen. So here, present, is it a tab, window, or entire screen? What is the thing I should change?
Entire screen.
entire slide. Okay, all right. Let me try that again. Are you able to see? Wait a minute. Are you able to see this slide? Second slide.
No, no slides are visible, sir.
One. Wait now. Are you able to see anything now?
No, sir.
I don't know. I'm sharing my entire. Choose what you like. Share. I don't know why I'm not getting anything. This is the problem with the Google Meet. I've not used Google Meet that much, So let me see. Try again. How about now?
Yeah, it's coming. Yeah. Please press F5.
But I'm not seeing that thing on my. You're presenting to everyone. Can you see Veda? How about this one?
Yeah, it's visible.
Okay. Next, are you able to see this one here?
Yeah, this was fine.
You were able to see earlier?
Yeah.
Okay, so now you see a compressible flow models here?
Yeah, but you were stuck on this 4 only.
I click on that.
Nothing was moving after that.
Okay, wait a minute. I'll just put that. I don't know why it is not going up. Okay, man. Wait a minute. Okay, let me just pick one by one then.
Yeah, that would be fine.
How about now? Are you able to see the compressible flow models?
No.
I don't know. What are you seeing now?
Just a blank. It's a black window coming.
What do you see? And do you see?
Yeah, now I can see slide on compressible flow models.
Okay.
And you have equations in the slides.
Okay. Let me. I think. Okay.
Yeah, you have to switch over in between.
Yeah, I think so. Okay, so just bear with me. So this is the.
You can move that meetgoogle.com sharing your screen. That bar you can move at suitable location. Don't stop. Okay, just move it. Yeah.
Okay. All right.
Done.
Okay, so this is the integral form of the compressible Navier-Stokes equations, you have the variables, conservative variables, the density, the momentum, and the energy. I won't be going, these are all you're familiar with. These are the viscous fluxes and the convective fluxes, body force. But the body force, I'm just putting it there, but most of the time you can actually define the pressure to absorb the gravity terms, okay, redefine the pressure. How about now, the second term, second slide, can you see? Hello?
Yeah.
Okay,
Yeah.
so this is in the viscous term you will find the viscosity, eddy viscosity, that will be modeled. You'll be introduced to that turbulence modeling by Dr. Madhukar later in the afternoon today. Okay, so this is useful if you're using LES and RANS models. But for DNS, I don't need to model all this turbulence modeling. I will just use the Navier-Stokes as it is. But for that, I require tremendous computational resources, which most of us do not have access to. This is a differential form. You can extract this from the integral form through a transformation. And this you can always see in the textbooks which you are reading. We would also encourage a practice of using scaling that is actually required to make the computation in a non-dimensional form. So by choosing this scaling parameters, you can show that the scaled compressible flow equations will look almost like the dimensional form, except that the coefficient of viscosity and all that will take a different value, and from there through suitable combination, Reynolds number, Prandtl number, and all that will drop out. So if I'm using a dimension form of equation dimensions, then I will specify, say, free stream 200 meter per second, and atmosphere. You'll specify the actual values, and you will get compute the values inside at all these cell points. But if I'm using scaled variables, then I will define my inflow conditions correspondingly. So 200 divided by the speed of sound will give me the Mach number, and then I have to multiply by the square root gamma, depending on what I'm choosing, and according to that you will specify it here. The choice is yours, all right? So you don't have to. So the differential form of the compressible flow, if I'm looking at Euler equations, I can throw away the viscous terms. If I'm interested in very high Reynolds number flow, viscous terms can be neglected, and if the flow is small angles of attack. So RE infinity, you solve the rotational compressible flow by solving the Euler equations, and this is where the first effort has been made to compute the Euler equations sometime in 1981, thereabouts. Now, for irrotational flows, I can make an assumption, irrotational contribution, where there's the vorticity. This is the vorticity del cross u. That will be zero. So that means that the u can be expressed in terms of a velocity gradient, and that phi. The phi is the scalar, as a scalar function, and that is termed as the velocity potential. And if you make this substitution in the Euler equations, you will get the unsteady potential equation like what we are familiar with in any textbooks, whatever, research papers. So if you're looking at a steady compressible potential flow, I have this one here, past an airfoil. This is my potential equation, and I can introduce a scaling, and that will scaling for the potential as follows, and that will drop on like that. I can make a further simplification, because if I want to solve this, I still need a mesh, okay? Because this is a nonlinear equation. It is a potential equation. I still need the mesh, which I would use for the Euler-Navier-Stokes equation. The only advantage is that instead of calculating all the variables, I would just compute just one velocity potential. So the other thing which we do is the small disturbance potential equation for compressible flow past the thin airfoils. So what you do is you assume that this airfoil is a very thin body. So if I put the airfoil in a free stream flow, it will just create some disturbances. And I write my disturbances in the velocity field as follows. So this is say the free stream velocity plus some small disturbance, and this disturbance will vanish as I go far away because you need to restore. And so I can write the thing in terms of a small disturbance velocity potential. I take all this and put inside my potential equation, and I work out everything, and I will get some equation like this. Up to this stage, everything is fine. All the red terms there, they are non-linear terms, and they can be neglected under certain circumstances. So the first such equations was the transonic small disturbance equation, where in this flight regime between 0.8 and 1.2, if you look at several parameters, you can actually drop out this. If you do an order of magnitude analysis, you can drop these two terms, and you're basically left with this equation. And this was the equation which was solved sometime in 1969, 1971. This is a very landmark effort by Merman and Cole, and that basically started the development of modern CFD technology as you see it today. Okay, so this was the first calculation where they solved the transonic small disturbance potential equation. Now for this, I don't need a mesh. My mesh will be just a rectangular mesh because the airfoil is replaced by a slit, which is a line, which is a slit on top and bottom. I will specify my boundary conditions. So the mesh is very easy to develop. And the trick here is this is a mixed flow. You have subsonic flow, you have supersonic flow embedded inside subsonic flow. So the computation of this was quite challenging for many years. And we will look into this thing a little bit later, what spurred further action. So the small disturbance equation, if you look, you can simplify it between 0 and 0.8. I basically get a simpler equation like this, which is like elliptic in nature. And for supersonic flow in this regime, some of the terms can be dropped out, and I will get this one. This is a simple model, and these are linear, the supersonic and subsonic flows, and you can get very elegant and quick estimates for airfoil. So these are the estimation based on linear theories, high subsonic and the low subsonic. This is what aerodynamic student will probably learn in school. Okay, so now let me go again to another. Are you seeing anything?
Yeah, the screen.
Okay, let me. Can you see the screen? What are you seeing now?
Yeah. Please make it full screen. Yeah.
What are you seeing now?
Yeah, I can see. We can see.
Semi-analytic approach?
Yeah, semi-analytic approach with.
So semi-analytic approaches, to solve this aerodynamics in this flight regime, you had the shock expansion theory, Rankine-Hugoniot. If I click on this, can you see anything?
Yeah.
You see
yeah, shock expansion theory.
Okay. So shock expansion basically, developed much, in the heydays. These are, if you think about the problem, you can come up with very elegant mathematical models and get some results. You simplify it in a very rational manner. And basically, this is based on the Rankine-Hugoniot. And with that, these are the basic tools. From the Rankine-Hugoniot, you get oblique shock relations. And the oblique shock relations in the vicinity of the weak shock regime, you can simplify it to weak shock relations, and that will give you the Prandtl-Meyer function for expansion waves. Where there are shocks, you have to apply the oblique shock relation based on the Rankine-Hugoniot. And where there are expansion waves, where the flow is expanding over a bump or something, I need to predict the variation of the flow using a Prandtl-Meyer function, and that flow will be considered isentropic. Okay, so this is what stood us in great stead for a long time, semi-analytic. The other one is the method of characteristics. It's no longer a method of choice. It is probably resting in the museum somewhere, but I think in the elucidation of boundary conditions for CFD, you still need some information on characteristics. So if I look at the potential flow model, steady state potential flow model, which is written in this manner, I want to find phi, but the phi is actually a function of x and y because I'm solving in the based on the exact differential. I can get two more equations, and I can put this equation in the matrix form, and then I can solve for all these red terms. And the way to do it is by Cramer's rule, and just take one example here, phi xy, and that is what you get. So all the other solutions will be of this form. You have a numerator and a denominator. And if you set the denominator to 0, that equation will give you the characteristics of this potential equation. And the numerator, if you set it to 0, that is will only happen if your denominator d is, the determinant of d is 0. Then you require the determinant of n to be 0. That will give you the compatibility conditions. Okay, so if you go and find from here, you will get along the characteristic line, the whole equation PDE actually reduced to an ODE of this sort. And that was what people have used in the 50s and 60s. And they have used that to write codes to develop the design of nozzles, converging, diverging nozzles of this sort. Okay, so we do not want to, but the details are all available in many textbooks. And then you have the Ekert's linear supersonic flow theory, which is again, this is the equation there. This is the linearized supersonic flow, which we have seen earlier. That this is a wave equation, if you see. So the general solution you can put like this, and it will have characteristics, which is going like this. These are the characteristics. And using that characteristics and the fact that the airfoil is thin, we can actually find expressions for the pressure distribution. And that's all. It's a very clever estimate here. It's by Ekert, Italian aerodynamist working with Ludwig Prandtl during the war, Second World War. And you basically have a pressure coefficient in terms of, if you know the shape of the airfoil, the upper and lower surface, that's all you need. This is the angle, that is basically the slope. Okay, so if you know the slope, if I give you a shape, you know the slope, you can find, and you can construct the pressure distribution. So that was how the state of the art was like during the early days. Okay, then we have a very good piece of effort by Cole, Julian Cole at Caltech. They wrote what is called the perturbation methods for transonic flow. And this is a very interesting book where they try to develop a lot of useful relations for airfoils and also for nozzles and various other things. And it's all in the transonic regime, which is really not that easy. And one of the things they were looking at is the transonic thin airfoil theory, the equation which is based on similarity analysis. There are many alternative forms. So the common Gooderly equation is what was focused by that. Now, beginning of numerical methods in 1928, Courant and Levy. Are you able to see this slide? Hello?
Yeah.
1928?
Yes.
Okay, so Courant and Levy basically demonstrated, some the notion of a CFL condition, which is called the Coran-Freire-Levy condition, and that came about from the analysis of the stability of a numerical scheme for hyperbolic PDE that was shown for the first time in the context of finite difference method. How do you derive this stability? You need to develop some idea about how the error in your numerical approximation will grow as you do the computation, because you need to select the spatial and temporal discrete values. So depending on how you choose and the scheme which you're using, some of these methods can become unstable, especially if it is an explicit scheme, and the implicit scheme are, conditionally stable, or some are unconditionally stable. But if you look at the literature, in 1944 to 1948, there's one guy called Emmons at Harvard University who was probably the first one ever to present a solution on the transonic flow past an airfoil and also in a nozzle. Okay, and the idea used shock fitting. If you look at the papers, these are the three papers here. They are basically using the velocity potential stream function approach of the Euler equations. They use finite difference method for the subsonic regions, and in the supersonic region, nobody really know how to handle, because there are a lot of characteristics there. So what it's called is that some numerical steering. So you need some knowledge of the characteristics in the supersonic region, and then you know where to fit the shock. Okay, basically where the shock occurs, the Rankine-Hugoniot condition have to be satisfied. So this is the solution he has obtained in 1944 using whatever technology that was there, and there was hardly any powerful computers then. There was probably some ladies were the calculators in Los Alamos lab. And so that's how this thing is a shock fitting. Okay, that is the first instance of shock fitting, and over the years, shock fitting lost out to shock capturing. We will come to that, but there is a book on shock fitting. There are a few guys work on the shock fitting. They're still trying to keep that alive because not many people. But it's very difficult to do it, especially for 3D flows and so on. But there might be some hope if you are looking at new developments like machine learning and all that. So those of you interested, you can actually reinvent yourself in that area if you have some interest. In 1947, Krang-Nicholson put the stability condition for practical use, and the 4950 von Neumann stability criteria for time marching parabolic PDE was established in a very rigorous form. Okay, around the same time, like 50s to 60s, PD lags developed shock capturing schemes for a conservative form of Euler equations for implicit compressible flow. Okay, so 59, if you see, Neumann and Richtmeier develop a notion of this artificial viscosity to capture shocks to overcome the limitation of shock fitting. Okay, but at that time, they were writing their Euler equations in non-conservation form. And then they found that the early finite difference method, like particle in cell method, led to shock smearing. So the shock strength is not computed accurately. And sometime around 5960, the Lax-Wendorf method alleviated this shock smearing method. So then that led to the famous McCormack method, which is actually a variation of the two-step Lax-Wendorf scheme. And for a long time, this method has been used for solving the Euler equations. And I want to talk a little bit about the shock capturing scheme. Can you see the screen now? Do you see a blue screen?
Yeah,
okay.
yeah.
Okay, so we go back to this question of nonlinear hyperbolic PDEs of this form. I just take a 1D equation. F here is u square over 2. And I have initial conditions here. So this is my initial condition, this light blue profile, which has a discontinuity at x equal to 2. And this is my x direction, and this is my t direction, and this is my u. I want to know what is my u, how it goes. So at different t, you will see this thing progressing along, So I want to know, how does this initial discontinuity propagate? Will it remain the same? Will it get dissipated? Will it incur? So that was the question people were asking at the time. So the lax scheme, okay, basically the lax scheme was one of the first one to capture the discontinuity. He put this in this is a conservative form. The non-conservative form will be del u del t u du dx, okay? F is u square over 2. So the lax scheme is this one here. The stencil is this. This is my t-axis, this is my x-axis, and this is my points here. Instead of using forward time and centered space, what he did is he took the average of these two and updated. Okay, so that's what he's doing here. And that led to some useful, so why did the result happen? So if you do a FTCS approximation of this leads to this, lax is actually replacing this two black dots with something in between. Okay, so and that's what, and you can do error analysis, growth error, and you can show that the solution is stable provided this condition is satisfied, and that's basically the Courant number. Okay, should be less than or equal to 1. Now, you want to know why it works. You know that when you do finite difference, you have the truncation error. So you consider the modified equation of the lax term, so that you include all. You take all the truncation errors and add it into the things. Okay, so into the finite difference approximation, you keep the leading terms. The higher order terms you can drop out. So if you keep it, that will be the modified equation. Okay, so this is the actual equation here, and then you have all these terms here. And there's this term here which comes out by keeping the truncation. This is the first order term. This is second order. So what is this? This you can do from the governing equation. You can do some manipulation to get this, and you substitute inside here, and you will see that you have this term here, this green stuff here. Okay, so that is actually an implicit dissipation term that is already built in by way of the discretization process, which you don't realize it, and you can't control it because it depends on the Courant number. So that led to the explicit addition of artificial dissipation terms. So I have my finite difference equation here. This is forward time, central space, discretization of this wave equation here, and then now I add a term here that is the artificial different dissipation terms, and that is the dissipative terms, second order terms. Okay, so if I assume an error and I substitute inside this thing and go ahead, I can find the error growth and see. Okay, so here there's an ellipse inside the boundary of stability. So if this axis of the thing is depending on the K2, which is here, and K1 is this constant here. So if I reduce K2 to 0, that's gone. It will become a line here. This ellipse will become a line. So for different values of K2, I can see where it goes. Okay, so it's important that for stability and all that, the ellipse fall inside the circular region. So this will give you some idea of how to control the K2, the artificial dissipation, because you really do not want to put so much of it, because then your discontinuity will be dispersed. Dissipated. So this is the question. When it propagates, if there's too much dissipation, it will become like this, so that the shock strength is not estimated correctly. And if there is spatial terms, it can also lead to dispersion, oscillations, post and pre, shocks. Okay, so that is some notion of this thing. Then in 1971, you have the landmark paper on the TSD, and what followed after that was an explosion. Jameson basically extended the idea of the Merman coal because Lax, in his forays into conservation laws, basically said that you have to put the differential equation which you're solving in conservation form. So if I have an equation like this, then the same law will be satisfied across the discontinuity. Okay, so these are jumps in f and g, and dy dx is the slope. So if you look at the form of the thin airfoil theory, the potential flow is given like this K is a similarity factor, and if you put this in the conservation form, you can put f and g as follows. Okay, so this is possible, but people abandon this altogether because after listening to Berman and Cole, Jameson extended the idea to potential flow. So this is our steady potential flow. And here he writes this potential equation in a different way. That is, he writes the continuity as follows. This is basically the U and V. You can write phi x, and the momentum will become this. This is, for the isentropic flow, the enthalpy remains constant. Okay, so H is basically this. And this is the jump conditions across a discontinuity. Okay, so that's what he did. And he developed a lot of beautiful codes in the 70s to 80s on potential flow equation on body fitted mesh, on aircrafts, in wings, missiles, you name it, everything, and the methodology based on this potential equation, such as multi-grid to accelerate the computation, put the CFD technology at a different level by the time the 80s came. So besides Jameson, there were a lot of other guys like Steger, Lomax, Garabedian, and Korn were also developing these solutions. Sometime in 68, 70, Lax van Droff used the Euler-Navier-Stokes. Yoshihara and Magnus used this scheme for Euler-Navier-Stokes, but the implementation was very cumbersome and inefficient, and nobody bothered about it. 76, 78, you have the famous Bing warming scheme, which is actually a second order implicit approximate factorization scheme on generalized coordinate, the implicit scheme, so they can run faster because if you're looking at the steady flows, you're not limited by, you're not interested in the transient, so you can take a larger time step to get to the steady state, but you can't do that for unsteady flows. So this is basically in the backbone of the famous Ames research code ARC2D, ARC3D, which later find itself in the overset grid solver. Okay, that is still available in the US, widely used. In 1981, the JST scheme appeared on the scene, and that basically changed the way in which compressible Navier-Stokes is being solved. The starting point of that method was a summer visit to Ricci in KTH. Ricci was using a McCormack scheme at that time. Okay, so what he did is he developed with a few others, Turkel and Schmidt in Germany, developed a three-stage time-stepping scheme, which he showed that it can be stable up to Quorum numbers of 2, because up to that time, Quorum number stability is limited by 1. Okay. So the group went on to develop a whole lot of innovative techniques, such as local time stepping, enthalpy damping, and so on. All that you can actually find by clicking here, Jameson's group, all his papers are there. You can have a look at it. But before I go further, I would like to talk a little bit about boundary conditions. When you discretize the solutions on a mesh, you basically get a system, the finite volume discretization basically lead to a system of coupled first order ODEs of this form. Okay, here is the gamma is the volume of the cell, W is the conservative variable, Ri is a nonlinear spatial discretization term, dissipation terms, everything, and M is a mass matrix. That is, people use cell-centered and cell vertex arrangements. There are benefits for both. We will talk about it in maybe a later CFD course or something like that. And for all this, that's how it is solved. And if you look at this first order, basically the Runge-Kutta method come to mind, and that's what people were using. The Jameson was using that. Okay, so now let me just talk a little bit about the boundary condition. Okay, I need to go further. So if I look at the PDE, most of you are familiar with the standard boundary conditions like on the wall, symmetry planes, everything. But when you deal with hyperbolic flows, hyperbolic systems, you need to worry about how you will set the boundary conditions at the upstream of the body and downstream of the body, at outflow, at the inflow. Okay, to get some understanding, I'm not going to go through a lot of mathematics, but if you look at the non-conservative form of the Burger's equation, that is of this form, and the conservative form will be this. Okay, so this is completely hyperbolic. Whereas the viscous Burger's equation is the same as the above, but I have a small alpha with a second order derivative there. Second order derivatives are supposed to be dissipative. Second order, fourth, the second derivatives, fourth derivatives and spatial coordinates are supposed to be dissipative. The third derivatives, fifth derivatives, they are meant to be dispersive. Okay, so dispersion and dissipation, these are also critical things to worry about when you are computing fluid dynamics problems. So Navier-Stokes basically is a mixed parabolic and a hyperbolic PDE. So if you look at the hyperbolic PDE, you will find that it has two characteristics shown here in blue line. This is the computational domain. Boundary data, I'm solving in between these 2 points, and there are 2 points here, and there's a domain. I want to know what is the value here. It is only be influenced by this gray color region, nothing else, okay, because of the character. If I look at the parabolic PDE, this hyperbolic, it is a degenerate hyperbolic in a sense that there are no characteristic degenerated to one characteristic, and that is actually parabolic, you march in time. Okay, so that's what we do, like boundary layer equations, they are parabolic. You start with some profile and you march. And the elliptic PDE, there are no characteristics. Okay, so if you look at the one-dimensional compressible flow equations in conservation form, I will, since this is recorded, you can read it. I will actually send you guys a set of slides which you can download later on. And if you look at the non-conservation variables, you can write the equations in this form here. So this is written in this form here, and the other one in this form, this is the quasi-linear form. This is the conservative Jacobian matrix. This is the non-conservative Jacobian matrix. Okay, what we do, we can do a series of steps here, but I'm not going to tell you. First, you find the eigenvalues of A, and you put that eigenvalues in another matrix diagonally. Okay, so this is a diagonal matrix, this lambda. Then you construct the right eigenvectors for corresponding to each eigenvalues, and you store them in rows like this. And that is your right eigenvector matrix. Then you find the inverse. Then you do a similarity transformation, and basically you decouple your original equation into the characteristic variable. So there will be 3 of that. Okay, you can do the details. Details are all well known. Okay, so what it does is it will give you 3 characteristics, and along these characteristics, 3 quantities will travel. So these are the information that is traveling along the 3 characteristics. Because why 3 characteristics? Because I have 3 variables. Okay, so if I have 4 variables, I will have 4 characteristics. And these are actually, if you look at it in a xt direction, you will get curves. Okay, so and along these curves, these are convected entropy and 2 Riemann invariants, and that is what we will use to guide our setting of the supersonic inlet, subsonic inlet, whatever. So if I have a supersonic inlet, then I will specify all the 3 conditions at the inlet. Okay, so that is basically, it depends on the whatever conditions there, you use that to calculate whatever. And outlet, you can see all going, you extrapolate the values of the flow variables from inside. Okay, for subsonic outlet, you have 2 conditions given by R plus and S, and one has to be extrapolated from the inside because you do not want some wrong value to be specified there. And subsonic outflow also, you see something is going inside along that characteristic, I want to fix the value there, otherwise it will bring some information into. And these 2 I will just extrapolate from inside. So I have the 3 variables, basically the 2 Riemann invariants and S, and from there I can do some manipulation. I have the 2 Riemann invariants, I can add and I'll get my velocity, field, pressure, everything. So that's how the boundary values are confirmed. One of the things which many people like to do at far field boundary is to ignore all these things and just say that, oh, the flow will just continue like that, 0 derivative. That's a very dangerous thing to do. If you put the boundary very close to the body, you're going to get all kinds of funny things. So as a rule, either keep the boundary very far away, which is not feasible most of the time, or use some other meaningful thing like a specified pressure boundary condition. Okay, so that is what I have to say about the like. If you look at the supersonic flow, I don't need to have a big rectangle over there because there's nothing happening here. So I need a truncated domain, and I specify my boundary condition according to those stuff there. Okay, so all these things are in the SU2 open source software. Can you see now? Are you able to see?
Yeah.
Okay, so this is available. The latest version is 7.10. This is what most of the time me and my students we explore. You can participate. They have a conference every year. Okay, so I hope some of you can do that. So that's about it. I want to say. Then the Turkel's precondition JST. JST is for compressible flow, but I can actually precondition the compressible flow to make it work at low Mach numbers, because at very low Mach numbers, the system will become very stiff if you just do like that. So preconditioner, basically what it does is changes the eigenvalues so that the speed of the wave propagation will be increased. And if you use a split level time matching, you can even handle unsteady flows. And the idea is very similar to Chorin's compressibility method. If you look at the incompressible equation, if you write it in integral form, it will look like this. There's no time-dependent term for the continuity equation. So what Chorin did was, because of that, the lack of time dependence doesn't make the system quite hyperbolic. So what Chorin did, which I thought was a very clever method when I first saw it, was to append some terms in pressure in front of the continuity equation in such a way that as you reach the steady state, that term will vanish. Okay, so that is called, you put a term there, and that P, that is the precondition. We call it the Chorin's precondition, which is this here. And you can see as beta goes to become a large value, this term will vanish. The same idea has been developed for compressible flows. So the JST scheme in SU2, you can also use it for incompressible, steady and unsteady flow. Just one code for all speed, because you have the full range of phenomena. Now, I do not want to, as time is running out, okay, there are actually today 85, if you look at 88, early 90, the full airplane code was developed using unstructured mesh by Jameson, and is widely used in Boeing aircraft and so on. And if you look at today, I think computing flows using Navier-Stokes Rand's model and all that are very well established. There's nothing new one could add in terms of research. So there are two types, shock fitters and shock capturers, and they were at each other's throat, just like the electric wars. The 70s and 80s, they were fighting with each other, but they established, the main man here is the Gino Moretti, okay, in New York University in the US. It's an Italian professor and engineer who did a lot of work in shock fitting. And some of his students still keep the flame alive. The tools followed up after Rowe's scheme developed for shock capturing, where the shock falls. So I just show you, I do not want to go into, because the time is already ended. There's some slides here showing shock capturing, but I would just like to just show you there are Riemann solvers, high resolution shock capturing schemes. Okay, one of the first attempts was called the flux vector splitting, okay, a scheme developed by this Sweeby, Anderson, and there's a Stanford professor also under beam and warming, they developed that, Steger, all right? So that was a very essential thing, because basically it limits the information that is traveling into a cell, like the finite volume cell. At the cell boundaries, you need to find fluxes. Instead of taking average, you find what is the amount of flux should be entering each phase when you're dealing with this kind of hyperbolic systems. So there's a whole lot of research, okay, which a body of research, which is very well recorded here in this book by Toro on various schemes for resolving the shocks. So you can see this shock here with high dissipation, this with very less or almost no dissipation. Ideal is to capture this red shock. So if you can capture the point to within 1 point, then the shock fitting guys were happy. Okay, so Rowe was the first one sometime in the 80s to show that. And Jameson has developed his own version called the convective upwind split pressure in the JST. So one could get shock resolved to a single point at this moment. So that's where we are at the moment. And although transonic flow and all that are for aeroplanes, missiles, trains, and so on, this workshop is basically for the environmental problems. You can actually look at the shallow water analogy. Are you able to see this? This is the Wikipedia website.
Yeah.
Shallow water may have relevance to the theme of the conference. So if you look at the shallow water, this is the shallow water equations. Okay, this is eta here is the height of the water above the ground, and the rho is the density. All right. So if you look at this equation, if I take the density out, density is a constant, then rho you can just either absorb it in eta or whatever, if you look at this equation, they are like the Euler equations, and so the same methods which has been developed by JST scheme, also SU2, can be used to study shallow water theory. Okay, so in non-conservative form, it will look like this, and you also have viscous terms added. So this is another area which some of you working in the environment might want to explore, because you already have an open source solver for hyperbolic systems. So I end my talk here. I think that's all I have. Okay. I'm done.
Yeah. Thank you, Murali sir.
I've taken full hour.
Anybody is having questions?
Yeah.
The floor is open for discussion. I think Madhukar Rao having questions. Yeah.
Can you hear me? Is my audio okay?
Yeah, I can hear you.
It's noisy.
Okay, yes, of course.
Hi, Murali.
Hello.
Hi. I was wondering whether you could comment briefly on the boundary conditions for the full potential equation, and also whether we need to enforce the Buddha condition for compressible potential flow.
Just a minute, there's a lot of background sound.
It's a lot of noise. How about now? Can you hear me?
Yeah, please say that again.
Okay, I'll write the question in the chat box.
Yeah, send the message. Comment on the PC, the potential flow. Say that again. How do I bring that one?
Hello, can you hear me?
Yeah, you were asking something about the. I saw the box, but where is the message?
Is my audio okay?
Now it's okay.
Okay. Can you comment on the boundary conditions for the compressible potential flow equation, especially I assume that all the boundary conditions shown so far for the solid surface and all were normal conditions. So is it going to be normal conditions over the entire field, or is there any point where you need to fix that?
You have the potential compressible potential flow equation as characteristics. Okay, so along the characteristics there are information traveling through the outer boundary. All right, so I can keep the velocity, the potential equation as it is. Px is u and Py is v. This is the potential equation. Okay, the potential equation is basically coming from the continuity equation.
Correct.
By taking into account the irrotation of the condition. And a lot of the time, if you look at the way we are taught, we will put the P inside the continuity and get the Laplace equation. But actually, if you look at Jameson's approach to potential flow, he doesn't even mention anything about the potential. He starts with the continuity equation. He says that is the potential equation, but my u is actually Px and v is Py. Okay, and because of that, I make the isentropic assumption. Enthalpy remains constant, so there are no viscous effects. Total enthalpy remains constant. Okay, so far field, I have the enthalpy. That enthalpy will remain the same in the flow field. Okay, the enthalpy will change if I have viscous effects. Okay, now I don't hear any background sound. Are you able to Hello?
Yes, yes. Yes.
Yeah, so the boundary conditions, if you look at the compressible potential flow, it has characteristics. So if I start, I know how the characteristics are oriented, and I know what information is traveling along the characteristics. Is basically, I showed a slide there for steady potential flow. Basically, is something like the Prandtl-Meyer function, which travels. So that will also be used to set boundary conditions at the far field, if you're talking about high subsonic, supersonic, whatever, mixed. But here, the potential flow is used to solve transonic problems. Okay, so you really need to look at waves which goes upstream and goes downstream. And then accordingly, you have to handle the stuff.
Okay. And do you need
We can take this up in the light of future work. There's a lot to be done here.
Okay.
I think you can add upon the wall conditions in case of the inviscid flow.
Yeah, the wall conditions are there. Basically, no normal flow on the body, and that information will propagate out along the characteristics. Okay, but we are not using any characteristic information. What we are interested in will be the conditions in the far field.
Yeah,
it's a free stream flow at that, but then there are some characteristics going upstream and downstream. So you need to take that in, because along the characteristics, if you look at the, you have velocities. There's a a differential equation carrying information. So based on that information, you have. Of course, we know what is the boundary condition in the far field. Is a free stream is untouched. Okay.
Okay, all right, good.
Questions, please.
Yeah, sorry, sir, can you please give some highlights how to solve defragmentation detonation problems using this compressible flow models, or is there any software who can assist in solving such types of problems?
Okay, that is a combustion problem, I guess, right?
Yeah, high
So
energy problems like detonation.
Yeah, you need to bring a species into play. Species transport.
We are interested to solve pressure profiles, how
Yeah.
it presents and then
So
it gets
yeah,
visible.
I have people using the compressible solvers in open form addressing detonation and so on. But you have to add some new information to it. You can solve the flow equations. Okay. SU2 basically solves the flow equations. If you look at SU2, I'm sure they have addressed some of these problems on using their software as well. Like for example, the entry of a body from outer space to the air, to the ground, it passes through the atmosphere. And so there is actually chemical reactions taking place during the journey. The air around the body will dissociate. So there are chemical equations, chemistry equations, which you have to integrate along with the fluid. So if I know the chemical processes, that is another set of equations that have to be integrated with the flow equations, and then you will have a model. For that, the time scales will be different for the two. So you need to pay attention to this. It's a multi-time scale numerical solution. But yes, yeah, compressible flow solvers have been used for this kind of issues. You can see in Fluent and so on. And I'm sure if you look at the SU2's site, there are a lot of people using that software all over the world. I'm sure some of them are using it for plasma related stuff and combustion problems. Okay, so the key thing here is the time scale for the process flow and the combustion process is different. So when you compute,
Is it freely downloaded? SU2 is freely available for download?
oh yes, the website is there. SU2, you can type SU2 on your computer. You can. It's been around for close to 8-9 years already. It's basically run by students of Jameson, and it's available. It's an open source software. You can write things and put inside, and we do that most of the time. Okay, so like you can look at it, SU2.
Thank you for the information.
Can you see the screen?
No.
So you just type SU2 on the website, you will get it. Wait a minute, what is happening here? Okay, I see. Wait now. No, I do not know how to activate the website on live and then show it. I don't think it's working in Gmail.
Yeah, maybe in the next section we can you can show that. I think so. So I think.
No, you just need to type SU2 on your website, and then you can see what is there. I mean, there is nothing to show. And the link in SU2 is in my slides. If it's clickable. So.
Yeah, it's available in Google. I mean, the one can search and get that.
Yeah, so it's an open source software, compressible flow. It can also be used to solve certain classes of incompressible flow. It is being used for a lot of problems, fluid structure interactions, you name it, it's all being done. Optimization, it's a lot of tools inside. So it's worth looking at.
So I think if there are no more questions, we'll stop the session. And I think Raj Gopal ji was trying to discuss with the participants regarding the installation of the software. If he is willing to, now we can ask him to discuss those issues. Mr. Raj Gopal?
Yes, Dr. Dirbude, I'm here. Can you hear me?
Yeah.
Looks like about 35 participants have already sent the host IDs. They've installed the software and sent the host IDs.
Okay.
Another about close to 20 based on the list of registrations you sent me. About close to 20 people are still to send it. But I see that some people have maybe already left for lunch. I only see about 38, 39 people on the chat. Can we do this? Dr. Rao said he can also show this during his presentation. But if not, maybe when we start the session after lunch, I can come online for a few minutes and discuss this with them. Once everyone is back. Because some of the people who have not sent the license, the host ID file may not be here right now. They may have left for lunch already.
Yeah, so maybe it is a good for when we will start at 3. You can take 15 minutes from, I think.
2 o'clock or 3 o'clock? I thought 2 p.m.
We'll start at 2 o'clock, but let the first presentation
Sure,
go.
sure. Okay, fine.
Then at
Okay.
3 o'clock we can.
Okay.
You can interact with them.
Okay, sure. I will do that.
Or maybe at the end of the.
Yeah, no problem. At some point,
better to have discussion between.
Yeah, Dr. Rao will also. I've sent him some slides. He will also discuss this during his talk. But I'm also available to if the participants have any questions about downloading or installing, I'm also here to answer their question.
Yeah, absolutely.
Okay, thank you.
So thanks, and we'll join at 2 o'clock. Okay, so thank you all for having a good time. I'm stopping the session now.